Hello, can you hear me online? Yeah, okay, thank you. Oh, what happened? Hello. Yeah, I thought it should be okay. Just mute that. That's very good. Very good. You just switch to.
Sorry.
Also need a water.
There's a bottle service. Each side, just take the bottle. There's a bottle.
Okay, thanks.
There's lots of water there and we'll get more also.
Okay, you will get started. See. Yeah, I think it should be okay. Let's get started. This voice needs to be reduced. Let me not touch this. Now, can you hear me okay? Everyone in the room? Okay, fine, good. So my name is Surhud and the faculty at the Indian University Center for Astronomy and Astrophysics in Pune. And today what I'm going to do is to talk to you about the galaxy luminosity function. Okay? This may seem like a very bizarre topic, but it's something that is extremely useful for astronomers. If you look at it, what does the galaxy luminosity function tell you? It just tells the number of galaxies of a particular luminosity L, and it's between say L to L plus DL. What is the number density of these galaxies? That's all it tells. Okay. So this number density, what does it mean? That there will be certain number of galaxies in a given volume. And so how many galaxies per how much volume, that is what this luminosity function. So if I tell you like this, then it may seem that, okay, this is such a stupid exercise, right? When you were children, you would have realized that you would go out and count the stars one by one. And that's exactly what it is, right? So the galaxies that you are counting them from that. Now the problem with this approach is that the universe is a little bit complicated. Okay, so first of all, the universe is expanding. What does it mean by distances in the universe? There are various kinds of distances. Which distance do I use when I calculate the volumetricity? So all of these things can be involved. Okay. The other thing is your eyes, for example, when you go out and try to look at the sky, you won't often see galaxies. Often you will just see some stars, unless you go to really dark locations. Then maybe a few galaxies you can see with your eye. But otherwise you don't. And the reason is that your eyes are detectors. Right? In some sense, they are acting as detectors. And so these detectors have finite sensitivity. It means that you cannot detect all the galaxies that are out there. And something similar will also happen with telescopes. So when you have a telescope, it will also have a finite sensitivity. And so you cannot see all the galaxies that are out there. So when you measure these galaxies, when you count this number of galaxies as a function of luminosity, you have to worry about the fact out to what distance could have actually seen a galaxy. And so all these things are a little bit involved, and that's the reason why I thought about at least talking about these things because in the tutorial session, what we will do is I will make you download a catalog of galaxies which has been observed from an imaging survey. The spectra have been measured, and then I will make you count these galaxies in the right manner, not in just one counting that one by one. Okay, so that is what our aim is. So our aim is to measure the abundance of galaxies, and the abundance of galaxies we are trying to measure as a function of the energy per unit time that they are going to give out. That's what is called luminosity. And we are going to do this in an expanding universe. So we first need to understand what do we mean exactly by an expanding universe. So let's try to understand that. So when Einstein came up with this general theory of relativity, initially he thought that the universe must be static. Because until then, everyone used to believe that the universe was static. But here is Einstein, he came up with all these equations, and then he's trying to come up with a model for the universe. What he finds is his model always shows that the universe is either expanding or contracting. He had to do something special to make it static. He had to, in fact, change his equations in order to make it static. So he was very confused. Why are these equations telling this kind of a changing universe? Until the time that it was Edwin Hubble, he decided to actually figure out observationally what is the universe. Rather than just thinking from a theoretical perspective, what I expect, he said, let me go out and observe and try to find out what the universe is. And in order to do that, what you have to do is you have to measure the kinematics of the universe. So you need to understand how galaxies in the universe that are present, how they are moving away or moving towards you. Okay. And depending on what distance they are. So let's take a simple example. Let's suppose that all the galaxies in the universe was not at all expanding. They were just lying around in some space. Then what do you expect? Okay, so there will be some galaxies which will be further away, there will be some galaxies which will be nearby, and then they will have some random motions because sometimes you see that there is another galaxy to which they get attracted, sometimes in this direction, sometimes in your direction, sometimes in another third direction. Right? So if the universe was not expanding, what would you have expected? That these velocities will have no correlation whatsoever about, as a function of what distance they are at. So you just expected some random scatter around zero. Some galaxies moving away from you, some galaxies moving towards you. That's all. And the way he measured these velocities was via the Doppler effect. So just like a train is coming and it's shouts a siren, and then as soon as it's approaching, it has certain frequency. As soon as it passes by, it has a different frequency. Right? So this change of frequency for light coming from these galaxies is what he used to measure what the velocities of these galaxies are. And these velocities are always line of sight velocity because things don't, I mean, moving on the sky, it takes a long time for galaxies to do that. So we don't really observe them on human eyes. So what you observe is only these velocities along the line of sight. So that is what he plotted on the y-axis here, that's shown as the velocity. It's written in kilometers, but in principle it's kilometers per second. Here ignore the seconds here, I don't know. And on the x-axis, there is this distance measure. It's called parsec. The first grid point is 1 million parsecs. This is 2 million parsecs. Parsec means it's about 1 parsec is about 3.26 light years. Okay, so light at its speed in vacuum, if it continued to propagate for 1 year, what is the distance that it would travel? 3.26 times that light year is what we call a parsec. Now, this is 2 million parsecs, and this is about 1,000 kilometers. So he got all these points here. He measured these distances using these stars, which are variable called Cepheid stars, and their periods and their luminosities have a certain relation. So you can think about them as light bulbs with known energy per unit time, known wattage. Right? And then you observe these stars and you see that they have some kind of a flux that they emit at your detector. What is the flux? Is the energy per unit time, but per unit area that is being incident on that time. So by measuring the flux and knowing the luminosity, you can figure out what the distance is. That's what he did. That's the distance on the x-axis. On the y-axis is the measured velocity. And when he did that, he found out that it's actually a straight line. So the velocity is proportional to distance in a positive way. Things are going further and further away. Okay? And the farther out they are, the faster they are. And then he said that well, the universe, our own galaxy should not be anything special. So if you look at it at these kind of relations from any other vantage point, you go to another galaxy and try to look at it, you should also see the same thing. By now, people are clever enough not to be very anthropocentric, saying that human beings or that we are shared out all these egos that we have, that we have to be at the center of everything. And so they say that, well, whichever galaxy you look at and you sit on that galaxy, every other galaxy should be following this kind of relation. And this can only work if the universe was expanding. So all the space in between all these galaxies, if it is expanding, then this is exactly what you expect to see. So just to give you an idea, let's consider a meter scale. And a meter scale has some gradations with markings, right? And let's suppose that meter scale now you uniformly expand. You are sitting, let's suppose, at the 50 centimeter mark. Then what happens is the mark which is just next to you, so something like 49 centimeter or 51 centimeter, within a certain amount of time, it will travel a certain distance. But things which are at 0 centimeter or at 100 centimeter, if you expand the scale uniformly, then it would have traveled a much further distance in the same amount of time. And so farther away things are, if the universe is uniformly expanding, then farther away things are, they appear to be moving faster. Okay? So please do this exercise once. Okay, you take a scale and then or you take a rubber band. On the rubber band, you put like 2 pins, okay, and then you stretch the rubber band and see what it does. Right? So pins which are further away, they will move faster away from you. And pins which are closer, they will move at a smaller speed. So this is exactly what he saw. And then he said that, well, Einstein did not have to think about making a static universe. The universe itself is expanding. And so he does not have to worry about it. These equations are nevertheless giving you these kind of expanding. So when you do observations, it actually helps you out, right? Because the universe actually telling what is going on, rather than you having to come up with just ideas to think what it might be. So observations are always better in that matter, that respect. If you look at Einstein, you would have also thought that maybe the universe would be contracting. If it was contracting, you would have observed the opposite behavior. These velocities would have been negative. Moving faster towards us at larger distances if the universe was contracted. But here we found out that the universe is. So then we try to understand what happens in these expanding universes. What do we actually mean by distances? Because when the universe is expanding, at what moment are you talking about the distance? Right? This becomes an issue, right? Because if you have a scale and it has some 0 to 100 centimeters written, you expand the scale in a uniform manner, then the gradations are still there. So you can measure just using the gradations and nothing would have changed. But the actual physical distance has also changed. So there are these variety of distances that you can define when things are expanding, which we are not used to in the Euclidean sense, right? In the Euclidean geometry that we take a look at. And so this is where I would like to start so that you have an idea of how we measure this distance. So if you look at these grid points, what these grid points are showing you is a grid which is set up on the universe, and this universe is expanding as a function of time. This A of T1, then T2, T3, T4. So you see that as time is moving on, it's expanding. It could have been the other way around, it could increase and decrease again. All these things are possible. But in this case, that's what it is. So now what I can do is, if I want to measure distances from this, I can say that I will use the grid points to measure the distance. So this is basically like taking that scale and whatever gradations are on that scale, you use that to measure the distance. Then you're fine because your distances, even if the scale expands or contracts, you can still use those gradations. And if nothing is moved on the scale, it will give you exactly the same distance. So this kind of distance is called the co-moving distance. A distance which expands or contracts together with the universe is called a co-moving distance. If you want to know what is the physical distance, then what you do is you take this scale factor and you multiply the co-moving distance. So think about that scale. So there is some markings on the scale. If you want to know at any point of time what is the physical distance, you have to know how much you stretch the scale and then what was the distance on the scale. Then you will know the physical distance. So physical distance is scale factor times co-moving. Now, how do you define this scale factor? That is also arbitrary, right? So the scale factor, at least the normalization of this scale factor, is determined by saying that the scale factor today is unity. So A of t today is unity. The good thing about defining things like this is that the distances that you will measure today, the moving distance today is the same as the physical distance. And then once things are expanding or have contracted in the past or something like this, then you can always figure out what the physical distance is if you know the scale factor. Okay? Okay, so now if you wanted to measure the velocities of galaxies, what will you have to do? Right? You have to measure the velocity of a galaxy is the rate of change of the physical distance. Right? And so what you do is you take the physical distance and the derivative of this physical distance. So the physical distance becomes the scale factor times the moving distance. You take now a derivative. So this you can apply a chain rule. Everyone familiar with the chain rule? So you take R moving out and you differentiate A by dt. So dA by dt times R moving plus A of t now you take out and then you take a differential of the R moving by t. So the physical velocity that you will measure, it will be a combination of these two terms. Now, these two terms have a particular meaning in cosmology. Typically, when what you are used to is just dr by dt, right, as a velocity. In the expanding universe, now we get these two different terms. This particular term is coming because of the change in the scale factor. So if the universe is not changing at all, that term would have been zero. But because the universe is changing, you will get this particular term. Okay? Now think about if objects on that ruler were also moving around. If they were moving around, then their moving distances change. And so that particular term is this particular. So the dr moving by dt, if objects were moving on that scale. So this object is called something called a peculiar velocity. This is called a cosmological velocity because of the expansion of the universe. That's what naturally comes out, even if the objects are sitting constantly on those grid points or on this. Now I can do some tricks. So this dA by dt is a dot. I can divide by a and I can multiply by a. Then what I get is a dot over a times r moving is r squared. So you get this particular term and this one I kept it as it is. So you see that the velocity is a combination of these two terms, the cosmological term because of the expansion, and the second term is the peculiar velocity term because of motions in between in the grid. Okay, on the grid. So let's suppose that these terms are quite close to zero. In fact, what happens is as you go further and further out, this term starts to dominate because it has some factor in front multiplied by the physical distance. So as you go further and further out, this term is going to increase. And so this term is more dominant compared to this term, so we'll just ignore this term. So now, what does that remaining term tell you? Its velocity is a dot over a times r physical. This is exactly what Hubble had observed. And the velocities of galaxies are proportional to the distances, right, with the proportionality factor a dot over a. This a dot over a proportionality factor is what is called the Hubble constant. It tells us what is the expansion rate of the universe. If you look at the dimensions of this number, what do you see are the dimensions? Can you tell me? A dot over A. 1/time, right? So this gives a time scale in the universe. You multiply it by C, it gives you roughly some kind of distance scale in the universe. So now we are starting to come up with parameters that you can actually measure and then connect to the universe itself, right? So the age of the universe, for example, it will be proportional to 1 over the Hubble constant, modulo some proportionality factors. All of the distances that you measure in the universe, they will be C times 1 over h naught. Okay, so C by h naught times again some dimensionless factors. So that's why this Hubble constant is quite important for us. And this again we will come back to it as we move forward. Now there's another interesting thing that happens when light travels in the universe, which is the redshifting of the wavelength of this light. So let's try to understand quickly where it comes from. So let's suppose there is a galaxy here and an observer here, and light is traveling from this galaxy towards this observer. Now all of us know that the light travels in speed of light, right? This speed which is constant per c. So the physical distance that light is going to travel at any given point t to t plus dt will be equal to c times delta t. So if we do that, I can write this c times delta t. So let's suppose it is at the time t somewhere here. Right? So then c times delta t will be equal to the physical distance it travels. What will be the physical distance? It will be a of t, the scale factor, times the moving distance that it travels during that time. Think about it. When light is traveling from here to here, this galaxy is so far away that the universe is continuously expanding. Okay, so when it is here, the scale factor is different. When it is here, the scale factor is different. When it reaches us, the scale factor is different. Right? And so I'm taking some time t in between. Okay, then this c delta t will be a of t delta. Okay. Now what I can do is, I know that light is consisting of waves, so there are crests and troughs. So I can take the first crest. Let's suppose that it was emitted at a time t. And it was received at this observer at a time tr. Now, if I want to sum up all these numbers, starting from this galaxy to when the photon comes to the observer, what I will have to do is, I will have to take this time-dependent thing below here, so c dt divided by a of t, and I can sum it up on both sides. So when I do that, what kind of sum do I have to do? I have to begin when the galaxy, when this crest left this galaxy, and I have to end when this crest reaches this observer. So those are these endpoints, T and. Now what I can do is, I can consider this next crest. It is emitted at the time t plus delta t, and it will be received at the time tr plus delta tr. So I can again do the same integral, same kind of summation. Instead of t to tr plus tr, I will have t plus delta t to tr plus delta tr. Okay. Is everyone with me? So now by the time this crest was emitted and this crest was emitted, universe is expanding, but the universe does not expand so fast. Right? So my A of t is not going to change that much in between these two points. So what I can do is, I can try to see that on this right hand side, I have exactly the same number, which is the moving distance between this galaxy and this observer. So this is the same. So now I can equate these two. So if I equate these two, what you will realize is it is basically a sum from here to here and a sum from here to here. These two sums can be equal, only these portions and these portions are equal. Because rest everything is exactly the same. Right? And so these two things, you can write it down in an integral form, and you can use also the integral equations of how when you have a limit, when you divide it into two, then how does the integral behave? In order to show that this thing comes out, that this c delta t divided by a of t, that small interval there, should be equal to c delta tr divided by a of t. That's what you do. Now, what is this c times delta t? So c is the speed at which this wave is traveling, and delta t is the time interval between these two wavelengths. That's basically the time period. So c times the time period will be the wavelength, right? So everyone with me, right? That's how we measure the wavelengths, right? So c times delta t will be the wavelength. And so what I get is that the wavelength at emission divided by A of t minus the wavelength at reception divided by A of tr, that is 0. Okay? And so what you get is lambda r by lambda e is A of tr by A of. So I'm just moving these terms on either side of the equal to sign and so on. So it's very simple. This is a very interesting concept, right? So what is happening is that depending upon when the light left that galaxy, what the size of the universe was, that defines how the wavelengths that I'm going to see will look like. The wavelengths at which things get emitted, let's suppose this lambda e, it does not remain the same as the wavelengths which I receive. The time intervals between those two crests at emission does not remain the same as the time interval between the reception when the universe is expanding. Okay. And the change that happens is basically a ratio of these scale factors. And so, if I look at a galaxy and if I can analyze the light coming from this galaxy, I can know what the scale factor of the universe was when the light left that galaxy, which is really amazing. Right? And so this lambda r by lambda e is something called a redshift or 1 plus redshift, in fact. And so this thing is 1 plus redshift. You see that the redshift is 0 when emission and reception happen at the same wavelength. If they happen at different wavelengths, then the redshift is non-zero. If redshift is positive, then it means that lambda r will be greater than lambda. So lines are shifting towards the red. That's why it's called a redshift. So that's the way it is defined. Everyone with me? Or am I singing the lullaby? I know after the food it can be tricky. So okay. So now that we have understood a few of these concepts, now let's try to understand how to define these distances in the universe. So it turns out that the universe is quite homogeneous as well as isotropic. And so in mathematics, there is a thing called maximally symmetric space-time surfaces or maximally symmetric surfaces. Okay? So these are surfaces which are both homogeneous as well as isotropic. And so we'll try to understand how to define distances on these surfaces. And because it's complicated to think about surfaces in 3D, we'll think about surfaces in 2D instead. So when you think about surfaces in 2D, if I ask you to tell me a 2D surface which is homogeneous as well as isotropic, can you tell me which of that? Circle. A circle is not a surface, right? A circle is a one-dimensional. I want a two-dimensional. A square, a disk. Any more ideas? See, a disk cannot be homogeneous at all points, right? If it is a finite disk, if I'm sitting at the center, then there is an edge somewhere else. If I go to the edge, it's not exactly the same, right? The disk does not look exactly the same. So, yeah, give me a two-dimensional surface which is homogeneous and isotropic. Surface of a sphere is one of these quantities, right? So, surface of a sphere, if you look at it, it's homogeneous as well as isotropic. Whichever point you go to, it's exactly the same, no problem. Much easier than that is an infinite plane, right? If you take an infinite plane, it is basically homogeneous and isotropic. Wherever you go, it's going to be exactly the same. It will extend out to infinity.
Zero curvature.
Yes, so we'll come into curvature. So if you take an infinite plane, so imagine this to be going all the way out. And if you wanted to measure the distances on this plane, then you can use simple Euclidean geometry. You get dl square is dx square plus dy square. But then you also told me that the surface of a sphere is also homogeneous and isotropic. So let's think about this homogeneous and isotropic surface, which is the surface of a sphere. Can I define a line element on the surface of a sphere. So in order to do this, what you can do is, you know how to measure the distances along a three-dimensional plane, right? So that is just dx square plus dy square plus dz square. But I am telling you that you cannot move through the sphere. Okay, when you want to measure the distances on a sphere, you have to move along the surface. So if you have to do that, what it means is your x, y, z, they cannot be arbitrary. They have to follow something called a constraint equation. So it has to lie on the surface of the sphere. So these x, y, z, they have to obey this kind of an equation. R square is x square plus y square plus x square. And that R is what defines the curvature, radius of curvature of this surface. You can think about the infinite plane also as a surface of a sphere, which has really large curvature. Good. So R square is x square plus y square plus z square. Now, this you may have seen before in your masters and so on, that whenever you have a constraint equation, you can simplify it and reduce the number of variables. So instead of x, y, z, you can say, let me go to theta phi kind of variables. And then what you will do is you will define z as r cos theta, capital R cos theta. And then x and y is r sin theta and cos phi sin theta. These kind of numbers. Right? The reason why you do that is when you square them off, then automatically this constraint equation is valid. Right? Because cos square theta plus sin square theta is equal to 1. And so if you do that repeatedly, you will see that you will be able to obey this constraint equation. So now you have a transformation of how to go from x, y, z to that theta and phi. So you can write what is dx, you can write what is dy, you can write what is dz in terms of d theta and d phi. When you do that and you combine this dl square expression, you get this expression. So your dl square on the surface of a sphere, it looks like r square d theta square plus r square sin square theta d phi. Is this something that you have seen before? I suppose you have, right? If you want to measure a distance, then you do all these r d theta kind of calculations, right? Or r sin theta d phi, depending on where you are, which latitude you are. So that's all it is. So I've just given you a way of deriving these things from first principles by going to higher dimensions. Okay, so the curved surface of the sphere was in 2 dimensions. We embedded this surface in 3 dimensions. We worked out the distance in 3 dimensions, but then we applied a constraint equation so that you always remain on 2 dimensions. So this is how you can understand curved surface. Now, what I'm going to ask you is to do the same thing but in 3D. So now in 3D, the surface of a infinite 3D thing, right? If you want to measure the distances, this dx square will just look like dx square plus dy square plus dz square. But if I say that I know now I want a volume, some 3D space, which is also curved. Now this is very difficult to imagine for us, but mathematicians have no problem. You can use the same techniques that we have used previously in order to go to a 4th dimension, and then I can add in a constraint equation, and then that will allow me to calculate what the line element is. How do I measure distances? And remember, these are distances. I have not talked about expansion at all here, right? There's no expanding things here. So think about it as distances on that grid, which is not changing. Okay. So moving distances is what we are talking about. Okay. So now what you can do is these constraint equations you can have of 2 types. Okay, so one is I can do dx square plus dy square plus dz square, either add a dw square or subtract a dw square. And depending on what I do, I get 2 different kinds of spaces. One is a positively curved space and one is a negatively curved space with these 2 different constraint equations. And now you do the same thing that we did previously. That you say that, okay, I have x, y, z, and w as variables. Now I will go down to 3 variables because I'm sitting on a constraint equation. And so you define your w as some chi, cos chi, and then there's sin chi, and then each of these cos chi, sin chi, you multiply the cos and sin six first. So once you do that, then you will end up with equations which look like this. For flat space, things will be something which is very familiar to you. D chi square or dr square plus r square times d theta square plus I square theta d theta. This is the normal volume element in Euclidean space, or not volume element, length element in Euclidean space, but in spherical geometry. That happens. Right? So similar to this, if you do it, if you use those constraint equations that I talked about, then for positively curved space you get something like this, and for negatively curved space you get something. So right now I don't have the time to go through all the mathematics, but I encourage you to actually write down and work through all these equations. It will be very simple. And what I will do is I will also send out my lecture notes, which will have some of these things given in more detail, so that you don't have to worry about writing anything down. Okay. Okay, so we get these two kinds of spaces. Now we'll say that, okay, what is this? What does it mean by positively curved three-dimensional space? Right? So this is very hard to visualize. So whenever you have hard time visualizing, try to calculate something simple. So one of the things that you can calculate is what is the area of a sphere, let's suppose, right? Do you know how you calculate the area of a sphere at a radius r? If you start from this kind of a length element, can you calculate what is the area of a sphere? Or let's suppose, forget about area. I want to calculate the circumference. Okay, so the circumference of a circle at a distance say I. How will you do that? Yeah, you see that, sorry, you can take this dl square, right? It's a length element that you need to integrate. Okay. Now, what is changing? So let's suppose I am on this circle. Okay. So only that phi component is changing. Theta is remaining the same. So d theta goes away. So I can forget about this d theta. I can forget about d phi because I am remaining on a fixed radius. So I can forget about the d phi. So now all that remains is chi square. Sin square theta I can always define such that theta is 90. And so this sin square theta will be 1. And so you get dl will be chi times d phi. And if you integrate over phi, so all 0 to 2 pi, you just get 2 pi times r. So that is the normal circumference of a circle formula that you are using. Right? Circumference of a circle is 2 pi r, depending on what the radius is. Now let's go to positively curved space and let's see what happens there. Interesting thing that happens here is now the same thing will happen. This d theta is 0, sin square theta is 1, and d chi is 0. Now instead of getting your 2 pi r, now you get 2 pi times r times this sin chi y. Okay. So now your radius, even after you go further out, your radius can become 0. Sorry, your circumference can become 0, even if you are further out. We will be like, what is going on, right? Because things are changing, it's looking very different. So what is going on? So in order to understand this, let's go back to our sphere. And let's suppose you are a person who is sitting at the pole here. And now you move further and further out, what you realize is, initially your radius is basically this distance from the top of the sphere to wherever you are going, right? And so you see that as you go on, your radius or circumference is increasing, also your radius is increasing. That's fine. When you are very close, it looks roughly flat, so it looks like 2 pi r. But as you go further and further out, it does not remain 2 pi. In fact, the funny thing happens is once you cross this equator, now your distance is still increasing. But what is happening to your circumference? It's actually decreasing. And in fact, it decreases, and when you come here, what happens? Becomes 0. So these kind of pathologies that exist even on the surface of a sphere can happen in volume, in 3D space. So this is how you understand. You have to do geometry in these spaces in order to figure out what exactly is the geometry of the universe itself. Is it flat? Is it curved? Is it positively curved? Is it negatively curved? And so on. And you cannot know this by just doing mathematics. You have to go and observe. Only when you observe this fact, try to figure out what is that, and measure things there, then you can figure out what the geometry is. There's no a priori value that it could have taken. It could be either of these. Okay, good. Now, the next thing is, so if I want to now measure a moving distance between 2 points, I have told you how to do this, right? It is just C delta T divided by A of T and integrate. Okay? From when the light came towards left in that galaxy and from when the light came towards. Okay? So that integral is over dt. You can always transform that integral to be over the scale factor. Okay? So dt you can write it down as dt divided by dA multiplied by dA. So then the integral becomes over dA. And this dA by dt term that you got in front, that is basically the expansion factor of the unit. So you can measure it just like Hubble integral. And so you can always do these integrals over A. The good thing about doing these integrals over A is that you know what the limits are. You know that scale factor today is unity, and you know what is the scale factor when the light left that galaxy. How do you know that? By looking at the redshift of that galaxy. Right? If you look at how the wavelengths are shifted, that can tell you what is the size of the universe or what the scale factor of the universe was when it started out. So by doing this, now you're transforming things into observable space, things where you can observe things and calculate what these distances are. Okay? The moving distances. But that moving distance also it turns out to be it's very hard to measure because this A dot over A does not remain constant. It changes as a function of time. How it changes is beyond the scope, right, of this particular term. I will show you roughly what it looks like. But that A dot over A, general relativity tells us that it depends upon what the constituents of the universe are. Okay? Think about A dot as the velocity, right? It's the change in rate of change of the scale factors. That's the velocity. So just like if I take this cap, not the line. I take this cap and I throw it up, right? At some point it reaches a velocity which is zero, and then after that it starts to contract, right? So similarly, this velocity in the universe of the expansion rate of the universe, it also changes depending upon the constituents of the unit. In this case, what is the force acting on this cap? It is that of the Earth, Earth's gravity, right? So in that case, it will be the gravity of all the constituents which determines how the velocity changes. So those are the things that we will have to work on. But again, we don't have time to go into all those details. But there are certain distances that you can measure directly. And these distances are what I'm going to tell you about. One is called the angular distance. So what is this angular distance or angular diameter distance? Let's suppose I have this mic and someone told me what is the size of this mic. Roughly how much? How much is this? Do you know? 20, 25 centimeter, 20 centimeter, let's say, right? So if I take this 20 centimeter object, okay, and you can start to measure what is the angle between your eyes, yourself, and this edge and that edge. If you do that, you will measure some angle. Now that angle changes as you move further and further away. If you are very close to the mic, that angle will be large. If you go very further away from the mic, the angle will become smaller and smaller. That's right. So what you can do is just by looking at the angle, and if you know the size of this mic, you can figure out what is the distance to this mic. The distance between this mic and you. Okay? So these kind of distances are what are called angular diameter distance. Okay? So these are either relations between the angles and the physical size, like this, so the angle of these edges and the physical size, or it could be a relation between the solid angle and the physical area of an object. So solid angle that is subtended by an object. You know what is a solid angle, right? Yes, no? Solid angle of a sphere is 4 pi. Okay, so it is basically a division of this entire sphere into smaller chunks. That is what is called a solid angle. Okay, it's measured in steradians or square degrees or square arc minutes. So these kind of units you will find. Okay. Okay. So what you can do is this d angular will be the area divided by that solid angle raised to square. The square root of that. If you had a one-dimensional object, then you will do that one-dimensional size divided by the angle. That's it. No square root. The square root is only applicable when we want to get from the area. Is that fine? So if you know the physical size or if you know the physical area and you can observe this object, then you can figure out what the angular diameter is. So that's one. So now what you can do is you can take the values that you have calculated for these distances in symmetric spaces. Okay. So if the universe is homogeneous and isotropic at all points of time, then it must have one of these metrics. But that metric can be multiplied by any scale factor as a function of time, and you are fine. It will still remain homogeneous and isotropic. If something is homogeneous and isotropic, you stretch it or contract it, still remains homogeneous and isotropic. Is that right? You have a balloon, or not balloon, but a sphere, and then you contract that sphere or you expand that sphere, it will still remain homogeneous and isotropic. Right? So the same thing you can do, k of t times the dl, and it will still remain homogeneous and isotropic. So what you can do is you can calculate what is the surface area of that sphere. And I told you that that surface area will be 4 pi times some function of chi. Either it's chi square or it is sine chi by r or sine hyperbolic chi by r and so on. So some f of chi is depending upon the geometry of the universe multiplied by the scale factor square. So this will be the physical area. And then the solid angle that whole area will subtend will be 4 pi. And so you divide the two, you see that d angular diameter distance is some f of chi multiplied by a of t. And a of t, the scale factor, if you say that the scale factor today is 1, then the scale factor at any other time is 1 divided by 1 plus h. So that's what comes out. And so you see that this angular diameter distance is some function depending upon the geometry, which you don't know, you need to figure that out. And then another observable, which is 1 plus h, which is good. So you can calculate what this angular diameter distance is and how it is related to that moving distance that we talked about, this guy. Now, what can happen is you can do the same thing, but with luminosity distances. Okay, so instead of using angles in order to measure the distance to this object, think about you having a bulb, a light bulb with a known wattage, and you can observe this bulb. If you take this bulb further away, then the energy that you get per unit area at your place, it turns out to be small. If you bring it closer, then it's a lot, right? And so the dependence of the flux that you see at your location, energy per unit area per unit time, and how it is related to the intrinsic luminosity, energy per unit time, that is what gives you the luminosity. And the formula that relates the two is this. The flux is equal to luminosity divided by 4 pi d square. So this is the normal Euclidean formula that you are used to. But because you are not in Euclidean space, you are things where space is expanding and contracting, things are going to change. And so you can calculate what it does by understanding what is happening to these areas, how these areas are changing as a function of time. There is another thing that you have to consider is that the energy of the photon, I told you that the energy, the wavelength of the photon increases. Do you know how energy is related to the wavelength of the photon? It's a c by lambda, right? And so if lambda is increasing, what will happen to the energy? It will decrease, right? And so all of these things, when you put together and figure out what is the flux, then you can show that this flux, the distance that you calculate with this relation, it turns out f of chi times 1 plus a is what. So again, there is a geometry dependence, but in addition to that, there is a redshift effect. Now comes the trick, right? You see, angular diameter distance is this, luminosity distance is something else, and covariant distance was just phi. And so there are these three different distances, and so you need to know what you are exactly talking about. So when you are connecting luminosities to fluxes, which distance do you have to use? The luminosity distance. When you are connecting angles to sizes, the angular diameters. And all of these quantities are related to how the A dot over A, or how the universe's expansion history is changing. Okay, so the scale factor is changing as a function. So if you can measure these different distances as a function of redshift, then you can know, you can not only constrain the geometry of the universe, but also what the constituents of the universe are. So that's how people actually go about doing cosmology. But I wanted to get to these cosmological terms because we will be using them in the calculations of the luminosity. So in order to understand how A is changing with time, you have to go to general relativity. And this is the equation of general relativity. And you have to take these metric coefficients of this dl square, all the things that we have written. We can use them, take derivatives and whatnot in order to get something called Einstein tensor, which is on the left hand side here. And on the right hand side, it tells us what are the components of the equation. So the scale factor and its derivatives will come here, and the constituents of the universe go on the other side. So when you equate these two, you can get some kind of differential equations which tell you how the scale factor changes as a function of time. Now again, we don't have time to go through these details, so I'll just give you what those equations look like. So there are two equations that come out from Einstein's theory of relativity as applied to that metric that we talked about, the length element that we talked about. If you take that metric and you apply GR, then you get these two different equations. One is an equation for the velocity, and the other one is an equation for the acceleration. So how is the scale factor as a function of time? What is the rate of change of that scale factor? This is the velocity, and how it depends upon the constituents of the universe. And then the second equation is telling you the acceleration of this scale factor, A double dot, and how it is changing as a function of time. So you get these two different equations. And if you combine the two, you get this particular equation, which is shown here on top. Okay, so it is saying that the acceleration of the universe is minus 4 pi g by 3 rho plus 3p by c square. P is some kind of a pressure to the material which is composing this universe. So let's suppose you have non-relativistic matter, then there is no pressure because this pressure is just the density times velocity square. And if velocities are smaller than the speed of light, which they are for non-relativistic particles, then that pressure can be ignored. So if you are in matter dominated rings, then this pressure can be ignored as this rho, non-relativistic matter. If you have relativistic matter, then this P turns out to be 1/3 of. Again, let's not go into too much of these details right now. But the one thing that you see is if pressure is always non-negative, if it was non-negative, then you should always get a deceleration because of this minus sign. Now, people thought that yes, indeed, the universe should be decelerating, and they started to observe the universe. And what they found in the 1990s was that instead of finding a deceleration, they found that the universe was actually accelerating. And in order to get an accelerating universe, now you have to hook up something where this rho plus 3p by c square is going to become negative. Now, the simplest way that people do this is by setting p is equal to minus rho c square. Okay? And when you do that, then you can see if you set p is equal to minus rho c square, then this will become rho minus. And so now that minus minus, so this will become minus 2 rho, and then there's another minus sign. Now it can cancel that, you can get an accelerator. So this is how people came to the idea of what the constituents of the universe may be by looking at these observations. It's not something that someone just thought about, let's put it there. It's all based on observation. Okay, good. So now those earlier two equations you can combine to get an equation which looks like this. So for any component of the universe, if you know how its pressure is related to the density, which is something called an equation of state. And so if you use P is equal to say W rho times C square, where W is some kind of a constant, then you can put it in this equation and you can figure out how the density changes as a function of scale factor. This may look a little bit odd, but I will give you some more physically intuitive explanation, okay, as to what is happening. Okay, so if someone tells me what is the relation between P and rho, then I can get rho as a function of A. Why do I need this? Because if I know rho as a function of A, I can substitute it here. Okay? And then I have an equation for A dot over A. I can solve for A as a function of time. If I can solve A as a function of time, I can get the moving distance, I can get the luminosity distance, I can get the angular diameter distance. All of these distances, then I can relate to what the constituents of the unit. So that's how it will become useful. So now let's think about some of these constituents. I told you for matter, pressure is 0 because rho v square is very small compared to rho c square. So P is close to 0. For radiation, P is rho c square by 3. So you take that. Did I say 3 rho c square? Last time it should be rho c square by 3. By mistake, I said that right. Okay, so P should be 1/3 rho c square. So now, what you have to do is, if you take this P max equal to 0 and you substitute in the previous equation, in this equation, so P is equal to 0, you see that d rho by dA plus P times rho by A is equal to 0. So this again, if you solve, use all your calculus things, you get d rho by dA, so d rho by rho is equal to minus 3 dA by A. If you integrate, d rho by rho is ln rho, and dA by A is ln A. And so you get ln rho is equal to ln A plus some constant. That's what you will get, right? So with the minus 3, in fact, right? And so if you simplify all of this, then you get this matter density going down as A to the minus. So let me give you an intuitive explanation for this. Let's consider a box. There is some matter inside it, and now the box expands to its volume by a scale factor A. Each of the dimensions is expanding by a scale factor A. How much will the volume increase? A cube, right? And so if the volume increases by A cube, what will the density fall down by? Again, A cube, A to the minus 3, basically, right? And so the density of matter, it falls as A to the minus. If you have radiation, now you are expanding your box. Yes, the number density of these photons will fall down. But in addition to that, energy of every photon is also falling down by one more factor of A. So instead of having A to the minus 3, now you have A to the minus. Okay. So everyone with me? Yeah. So depending upon what the constituent of the universe is, whether it's matter or radiation or some other things, then this rho will depend upon the scale factor. And that dependence you can plug into that equation that I showed you to figure out how the scale factor changes with the function of time. And that is very fundamental because if you know that, then you can calculate all these distances. In reality, what we do is the opposite problem, which is that you have measured these distances. Okay? And if you change these components, you can get a different distance as a function of redshift, right? So you try to change these components until you get a good match to your observer. Because you want to fit to your observables. You want to know what is the universe like, which gives that kind of distance redshift relation. And so the constituents of the universe you can learn by looking at this kind of observables. So everyone get me so far? Okay, so this is mainly the kind of things that I wanted to show you. So let me just flash the equation that we use. So if you look at A dot over A the whole square, this it turns out to be H naught square times these different quantities. Okay, and let me explain all of these quantities to you and what do they mean. Okay, in reality, you look at this equation, what do you see? You see A dot over A the whole square. What I've done is I'm taking this to the other side. Okay? AC square by A square, that I took to the other side. And I have a 8 pi g rho by 3. What I can do is I can measure this expansion rate of the universe today, right? A dot over A is something which is observable. I can measure it today. That thing is called a Hubble constant. But this is the general A dot over A at any point of time. So I cannot substitute that H naught here. But what I can do is, using this H naught, I can compute a density which will tell me what is the geometry of the universe. So let's try to understand how. So let's suppose I look at this equation today. Today, A dot over A is H naught square, right? So this is H naught square. H naught square plus AC square by AC square is equal to 8 pi 0 by A. A is equal to 0 when the universe is flat. So if that is the case, then what I get, when the universe is flat, my density and my H naught square should be related by this equation. So if my density is equal to 3 H naught square by 8 pi G, density today, then I should be living in a flat universe. This is how I know I can measure the geometry of the universe. I measure the expansion rate and I compare it to the critical density or density which I can make up by using some fundamental constants, 8 pi G, rho, 3, right? These constants and the Hubble constant. And I compare what is the actual density in the universe to this density that I calculate. And if it is equal, then this A should be 0, and then you should be in the flat universe. If the density is larger than the critical density, then if this density is larger, then what will be K? K will have to be a positive quantity. So then you are in a positively curved universe. If the density is smaller, then you are in a negatively curved. This is how you can measure actually the geometry of the universe. Isn't it cool, right? We can actually learn about the universe by measuring out all these things in the real world. Okay, good. So let's suppose that you know what this kc square by a square is. You can figure out what the geometry is. Then what you can do is you can take the critical density, which is 3 h naught square by 8 pi g, and you can take it out from this particular fraction. So if you take that out, then you will have a rho divided by rho rate. Okay, so all the densities divided by critical densities. Those are things which are called density parameters. Okay, so that gives a dimensionless number which you can work. Those things, dimensionless numbers, are called operators. So if you take this equation and you take the rho, and instead of rho, you say that there are many different components of the universe. Some is radiation, some is matter, some is this weird component which gives an acceleration, right? So all these are possibilities. So you put them all together as the right hand side of this equation. That's when you get this kind of an equation here, right? So this omega n is nothing but the matter density divided by the critical density. And then this a to the minus 3 factor, where is it coming from? The density is changing because of the expansion of the wall. That's why this a to the minus. Similarly, there is a radiation today divided by critical density, a to the minus 4. Then this weird component which had a W equal to -1, I thought, but a W can be general also. So I have just kept it as a W0, and then -3 times 1 plus W. And then the K by A square that I had, I converted into a quantity called omega K divided by a to the minus. So you now get this beautiful equation which is related to the Hubble constant square, something you can measure, and then these parameters are things that you want to measure, and this A dot. So you set up an inverse problem. And you can always calculate how the luminosity distance as a function of redshift will look like, or any of these distances as a function of redshift will look like. You can compare it to the observables and then figure out all these quantities. What is omega? What is this? What is this? That's the beauty of doing cosmology in general. Okay, so you will notice that oftentimes this is assumed to be 0 because radiation for nearby observations, you don't need to worry about radiation. This is an extremely small number. As you go to very early universe, you have to worry. For the moment, we'll just ignore it. Omega K, the universe has been observed to be extremely flat, very close to flat. basically down to the precision that we can measure, it looks flat. And so this omega k to the minus 2 also I can remove. So the terms that remain are omega n this, omega w this, and that's it. That's the equation. So if someone tells you that, okay, let's write down the model for what the cosmological model is, then what all things you need to specify? You need to specify h naught. You need to specify omega n 0, omega w 0. Okay? And what this w is. So oftentimes this w is taken to be -1. It's this dark energy as it's called. So when w is -1, 1 minus 1 is 0, and so this a to the minus 3 times 1 plus w is not required. All you have is this omega w or omega lambda. So I can specify omega n 0, I can specify omega lambda 0, and I'm done. But there is one more trick, which is you take this equation, evaluate it today. Then today k dot over a is h naught square, exactly. So h naught square is equal to h naught square times this. Then h naught square will cancel out. So what you will get is 1 is equal to omega n 0. A is 1 today, so a to the minus 3 is 1. So omega n 0 plus omega. So there is also a constraint equation. 1 is equal to omega n plus omega lambda because we are living in a flat. And so what that means is I don't even have to specify this. As long as I specify omega n 0 and h naught, I'm done. Okay. So when in today's data tutorial, we'll go back and do set up a model for cosmological model. The two parameters that we will have to give when we are in the flat universe will be omega lambda and h naught. These two are the things. That's it. Okay. Okay. Everyone with me so far. So our aim for today is to measure the luminosity function of galaxies from the gamma survey. So gamma is this galaxy mass and assembly survey. From this, we are going to measure this luminosity function. We will use the following Python libraries, AstroPy and NumPy. The steps to follow will be to download this data from the gamma survey website. It can be done using geo tools, but I'm just going to directly give you the URLs to these files. Okay. These are like 100, 200, 300 megabyte files. But they can be also downloaded using geo tools and SQL libraries and stuff. Sorry, SQL commands and so on. But we'll do it plain text files. Then we'll visualize this data to understand its features. And then we'll learn a technique to measure this luminosity function of galaxy. Okay. And after the tutorial, if you have some time and energy, then you can do one more homework, which is to connect it to theoretical models of something called a halo mass function. So just like you can count galaxies in the survey, you can theoretically predict what is the number of dark matter blobs which can host this galaxy. Right? And when you connect them, you can learn about the connection between galaxies and these dark matter. So this is for something later for you to play. Is that okay? Okay, let's see how much time we have. We started at 2:30, right? So 1 hour, 7 minutes have passed. So maybe another 10, 15 minutes I think. Is that okay? Yeah?
Sorry, T has arrived.
Oh, T has arrived.
There's a question on the chat.
Oh, yes. Yes. Maybe I will take the first question here and then, yes.
Sir, you were talking about the density, like you were saying that you're taking on the component, gas component, and the thing. For example, we are trying to understand the non-baryon.
Yeah.
And it is not connected with, we cannot do it live. So there is no such connection. But if you want to understand the what the continuation of non-baryon component separately on the expansion data, expanding first, how you understand?
Right. So the question is, I will just repeat this question for people in the online audience. So the question was that how does how can we distinguish between what is matter component, what is this dark energy component, or what is the baryonic and the non-baryonic component? It is very difficult to do that.
And just distinguish we are trying to understand how it will affect the expansion rate.
Yes, yes. So how it affects the expansion rate is something that is told to us by general. As long as you can plug in the parametric component there, it's not a problem.
Because we do not have any established ways to line and non-line.
That's fine, but we can model it as a macro component which does not interact with light, but it still has a density. And we model it with its density. That's it. And then we try to measure what this density. And just like ordinary matter, we'll say that as volume increases, its density is going to fall down as one over. Now, if you change the components, so this omega n, if you make a lot and there is no omega lambda, then the universe will behave in a particular way. So especially the scale factor, it changes like t to the 2/3. You can solve these equations and say that there is only omega matter. If that is the case, then you will see that A is constantly A is proportional to t to the 2/3. If instead there is only omega lambda, then the A of t comes out to be exponential related. So the longer you can map out this A as a function of time, then you can even start to distinguish how much exactly is omega, how much exactly is omega. Okay, what was the question in the chat? Photons to lose energy in its flight. How is it included in the redshift pipe? Photons lose energy in its flight. They don't lose energy. In fact, if they are traveling from one place to the other, the wavelength of the photon does not change unless the universe expands. Only because the universe expands that you start to see this. Otherwise, a photon will always maintain the same thing. Okay, so then what we'll do is we'll stop here, take a break for tea, and then after that we'll come back. I will finish up some of the slides and go through the tutorial. And I will give the Python notebook anyway, so you can take a look.
Yeah.
Okay.
Thanks, sir. Thanks. I have to travel here forms of here. I'm putting in these things that you submit your tickets and all that stuff. Okay. And on the back side of it, please put your bank details. You know, because all the transfer will happen on the application. Nothing is happening in cash. So you'll submit all your stuff and later on, it will come out. Your bank. But there's Xerox of your tickets for that. And obviously, as per the rules I told you, right? MSc to MSc sleeper, research scholars, BSc, have to keep it. Okay, so please pick up your form and submit it latest by tomorrow here. Before you go, you don't submit it, then you go. Simple. Yeah, thanks. So please pick it up from there. And 15 minutes chai, right? Chai is already out. So we are 3:40. So by 4 we start.
Yes.
4 o'clock leave. In 20 minutes, please come back. Yes, it's obviously.
Second basis.
No. Second day sleep nahi bhaiya. MSc को भी sleeper class. No. I don't. Just finish. Go ahead, finish. जो भी है, वो हिसाब से. And do it. Okay. You want to give it. Oh, you won't submit them. Otherwise, you won't get. We need your physical signature on it. So later on, I can't do through email. So, chai is ready. Please come out. Chai.
Yeah. We are not sure about the double constant value itself. Right? Like for the early engineers, it's saying like it's a lower value, and the late engineers we are kind of taking us like 74. Exactly, I don't remember that. Yeah. Like, then how we are like considering that value? Which value we are considering by doing this all the shifts?
Yeah, so for the moment, what we'll do is we'll assume it to be 100 kilometers per second per megaparsec. And then the true value will always be 100 times h, small h.
Yeah.
And that small h you carry over in all the calculations, depending upon what you want to say. So whether it's 0.67 or 0.74, you put it and then you can get the observables. So oftentimes the luminosity distances are not measured in megaparsec. They try to measure it in H inverse megaparsec because they don't know exactly what the absolute magnitude is. So I told you that the mic you can measure this if you had been given the length. But let's suppose nobody tells you what the length is, but they tell you that I know that it is going to be of the same length,
Okay.
but they don't tell you the length.
Exactly. We don't know.
Then it becomes a completely degenerate problem.
Ah.
H naught and this length will be completely degenerate. Okay. So supernovae, they are standardizable candles, and then people um, completely say that, okay, I don't care about exactly what the magnitude is. If I care about H naught value, then I need to
Then-
know what that
yeah,
magnitude
exactly.
is. Then people use these nearby observations of Cephids, calibrate all these things. And that's where all this
Yeah, that's the
confusion is
confusion,
coming
yeah.
from. But we'll have to see. I mean, nobody knows whether the value that you get from the early universe, whether that is always going to be an extrapolation to today. The expansion rate that you will get.
Yeah.
So it is model dependent. So if the model changes, then this
Then
value
the
can be
value
changed. While the direct observations that you are making with Cephids, they are direct measurements, but they are prone to systematics. So we don't know whether it's systematics or it's the cosmological model which is different. So you try to make your inferences um, um, as much less susceptible to these problems as
Model-
possible.
okay.
Yeah.
Model
The problems of H0.
Because I was trying to work on the stochastics of the new latest paper.
Yeah.
Gravitational wave background.
Yes.
Where they are proposing like new way to find the H naught.
Yeah.
At least we will get the correct part.
Yeah,
Is
yeah,
it,
yeah.
lesser or is it higher or?
It's going to take quite some time though, using gravitational waves,
Yeah.
but yeah, I mean, people are working.
There was like
Yeah.
last month they said there was.
That's right.
I was trying to work on that. Like, there is a difference in that. Like if we take the gravitational background also, it will also be a model dependent on.
Yeah, so there are certain things which are less model dependent than us. So
Yes, it
more
will
than the
plus-
stochastic thing, if you take neutrinos, for example, binary neutron stars, sorry. So these binary neutron stars, you can see a counterpart. And the gravitational waves, depending upon their amplitude falls down as 1 over dl. And so you can measure the luminosity distance by looking at the amplitude. And if you can find the counterpart of the galaxy in which this gravitational wave will happen, then you can get a redshift. So you have distance redshift, you are in business. Just like Hubble did. And so that's the best way actually forward. But people try to use even binary black holes where statistically we try to figure out what the redshift is. It's a big growing field. So yeah, each one has its own merits and demerits, pros and cons. And what will be the most interesting is multiple of these methods then give the same answer. Then you know which one.
It's not giving.
It will take time. So yeah, I mean it's a known problem and it's a problem that many people are working. So yes, hopefully you will find answers.
Yeah. Trying to work on this.
Yes.
Thanks.
Yeah.
During the derivation of sol in general relativity, I would say those time but provide scale factor. You have assumed that a scale factor is your
Yeah.
why not other
Yeah, very good question. So because we have observed the universe to be homogeneous and asymptotic, this turns out to be the best coordinate system to describe things. So where the things spatial hypersurfaces at constant time are homogeneous opacity. Because that's what the universe looks like. So if there is symmetry to the universe, then we should go to uh, a coordinate system which utilizes this.
Yes.
So this particular coordinate system utilizes this. That's the reason why it is like that. So see, if you are in an isotropic and homogeneous space, if you do some kind of transformations, then you won't remain in a homogeneous and isotropic. And so then you will not use the symmetry of the system. So to use it, you can show uh, uh, you can show by using the homogeneity and isotropic metric that you can simplify the metric to look exactly like the one. It's called a Friedman product. But
And last one is we see a gravitational redshift.
yeah,
So how do we measure that there is a gravitational?
yeah. I mean, you need to shoot out photons from some. I mean, there's this experiment called Pound replies. And they either drop the photon from high or they, yeah, they put it to the top and they saw the red shifting of the frequency. But in real, I mean, in astrophysical senses, people, what they do is they look at a cluster of galaxies, and this cluster of galaxies is sitting in a massive dark matter halo. It's a dark matter blob which hosts these galaxies. So depending upon whether you are at the center of that cluster or you are in the outskirts of that cluster, you travel through less potential well or more potential well. And then just by looking at the behavior of these redshifts, you can figure out the gravitational field. So look for paper by Wojtak, Wojtak, Ladislav Wojtak. They have this, and then Shadab Alam also had a paper. There are multiple papers for this. Wojtak is a nature paper. Oh, thanks.
You had mentioned that, like.
Sorry, they were also trying to
Oh,
ask
yes,
some
okay.
questions. I could come to you.
Very silly doubt, but the space between the galaxies, it is expanding. Space is expanding. But what about the space inside the galaxies?
Right. So the galaxies themselves is composed of stars, and the stars are now stuck because of the gravitational forces in between them. And so these stars, they don't actually move around because of the expansion. But the galaxies, we start to see them. Now, this only holds if our omega lambda guru is just being lambda equal to -1. If the W is not equal to, sorry, if W is equal to -1, W is not equal to -1, in fact, something smaller than -1, then eventually even these stars will get ripped apart from the galaxy. Not only stars getting ripped apart, even the atoms within the stars will get ripped apart. The nuclei will get ripped apart and so on. So it depends upon the behavior of this expansion. It's not something, it's basically these gravitational binding forces versus this expansion.
That gravitational bending forces between the matter.
Yes.
What about the space between them? It's like the space expanding and the matter is.
Yeah, so the space will be expanding, but what you can measure is what is happening to these.
Yes, between
And
these
that,
two matter
yeah, they
points.
will just stay.
They will stay the same distance, but the space might be expanding, like is expanding.
Space is expanding, I mean, it will expand and just go somewhere else, but yeah.
But that
the
distance
objects,
is limited.
physical distances. Yes.
Yeah, you were saying about that question that.
Ah,
the
yeah, yeah,
wavelength
yeah.
changes, energy will.
Yes,
remain
yes,
same.
yes.
Energy will remain different. There's this one technique.
Yeah, sure, sure. Yeah, of
There's
course.
no
Yeah.
time translation symmetry.
That's right. So when I say lose energy, its
Yeah.
energy goes down. Physical
Yeah.
energy goes down. That is true. Where does it go? We don't know.
Yeah.
It does not have to be
Energy
conserved.
conserved,
Energy
yeah.
does not have to be conserved.
Yes.
In GM. Yeah.
Yeah, it's
That's
only
fine.
like, I think we define it for the locally inertial frame, there it is constant. In the local.
Yeah, indeed. And that's the
Yeah.
same thing. No? So
Yeah.
because the universe will not be expanding. So when you consider a small amount of time dt. And so there your photon is not going to lose energy.
2 weeks ago, in our institute, IIT Tirupati, one of Ayuka's professor gave lecture on cosmology too. I think his name was Professor Hasan.
Yeah, yeah.
Yeah, he came to our IIT to
Yeah, yeah.
2 weeks ago.
Okay.
He was giving lecture on
Cosmology.
cosmology, and he introduced this BAO, where
Yes.
we're running acoustical oscillation.
Yeah, you can measure the angular diameter
Yeah.
distances. Yes, yes.
So I met him during.
Okay, cool, cool.
lecture.
Yeah,
Yeah.
he's our colleague.
So do you know Dr. Vikram Khare too?
Yes,
Oh, he's our faculty.
yes,
there.
yes, yes.
So he's also one of our mentors.
Yes.
Uh,
Excellent. So you're working on
I'm not
IGM
working.
and so.
No, I'm not working. Dr. Vikram, he is one of our teacher.
Yeah.
I'm working in Dr. Aniket Joglekar.
Okay.
Who's in IT Tirupati. I'm mostly working in this neutron star heating.
Okay.
So I wanted to know about all this data stuff.
Okay, very good. I hope
Interested.
things are
Yeah.
okay and followable.
Yeah.
My worry is always that it gets pitched at too high a level, then nobody understands. So
Okay. It's nice.
as long as things are understandable, it's fine. It has to be a little bit fast though because of the time.
So we consider our,
Let me drink water. Huh? Yeah, you continue.
yes, so we consider our space as a flat space in general, but what is the idea behind that? Is the best case scenario, because there's a critical density, if it's less than the general density, so it becomes a negative or the negative cause. So how does that one can visualize that there is a negative cause space?
Visualizing is difficult. So almost impossible. That's the reason why.
Some kind of parabolic or hyperbolic structure.
Yeah, so it requires something like a saddle.
Saddle hyperbolic.
Yeah, so it requires saddle, but again, the saddle that you are seeing is in 2 dimensions, right? So you need to think about 3 dimensions. Now, how do you think about a 3-dimensional saddle? I don't know. So, visualizing is hard. So that's the reason why the way I introduced it. I did not, you did not really visualize, you did just go through.
So in general, those things are just technical or mathematical expressions. They have no direct correlations or.
No. Our universe could have been positively count. Would have been negatively count. It could still be because there are always error bars, right? It is flat to within some accuracy. In reality, it could be still false. So it may happen that you continue to go and you continue walking in that same direction, you will come back. That can happen in a closed universe. And our universe may be closed. It's just that it's a very large curvature, whatever it is. So it will take for a long time. But it can happen.
Hello. Hello. Yeah, so once again, I'll repeat, these are the travel forms, okay? So all of them have been promised travel attendants, assistants. So please fill up your travel form and submit it before you leave. Okay? If you cannot even submit it with here, you can leave it in your respective guest houses also. I will put that form there. Okay? So please
Should I give
just
you?
get the travel forms. Number two, if you remember, tomorrow in the evening, we are having a sky watching session. Okay? Which will be in the terrace of this floor itself. So we'll have our sessions and then we have the sky watching. And then we'll have dinner at your respective guest houses like that. And Surhud sir has a flight to catch. That's why I got your back faster because he cannot flee today. So let's start with him and
Yes,
then
See, there are some questions.
yeah, I already answered. I answered as you.
Sorry? अच्छा आज नजमात से नहीं अरे यार
Hello? Yes. Good.
There,
Now that you are wide awake after the tea, now we can go ahead and measure some galaxy luminosity. Um, So before we move to the actual data section, I wanted to tell you.
that's the one.
This is done.
This is that.
Yeah, that's done.
you answer it. You are you
Oh, no, I will share. I
It
will-
is in his control, not mine.
Let me share.
You are focused on
Yeah, it's fine. I have done the right. Okay, so, I told you what our aim for today is going to be. And, sorry, I had to give this background of cosmology in order to get towards our aim, okay? So, let's see. Is this not moving? Okay, so what you are going to use is this gamma spectroscopic survey. So this survey was done with the Anglo-Australian Observatory. It's now called Australian Astronomical Observatory because I think England pulled out of the funding for this. But at the time when it was done, it was called the AAP. Still the same acronym, AO, sorry. And what this observatory has is a nice spectrograph. So what is a spectrograph? You take a light and then you put it and it disperses the light into its wavelength components. Why do we need this? What's the answer? You know this, right? Because we want to measure redshifts. Okay, because that's one of the things that we want to measure for these galaxies is the redshift. And if we can measure the redshift and if we know the constituents of the universe, then we can combine to figure out what the distance to these galaxies are, what the luminosity distance is, what the angular diameter distance is. All these numbers we can calculate. So what this survey has done is there was an imaging survey run by something called the Sloan Digital Sky Survey. So this sky survey, it imaged a large portion of the sky. Then it took some of these portions and said that all the galaxies that I see above a certain flux, I'm going to target it. And I will put a fiber on it and measure the redshift for this galaxy. So this way, they measured redshifts for many, many galaxies, and those are the redshifts that we are going to use. So that survey is called as gamma survey. Okay, so in an imaging survey, I said that gamma uses this imaging data from SDSS. When photons from a galaxy with a certain luminosity L. So L, what is L? Luminosity is energy per unit time. So when they arrive at Earth, what you have is a detector, and that detector is going to intercept some of this light which comes from that faraway object. So what you can measure is the number of photons you receive per unit time per unit area. For that detector area. Okay, so that is what is called a flux. So this traditionally this flux is measured in terms of astronomers do it in terms of something called a magnitude. Okay, so this formula you are used to now, flux is luminosity divided by 4 pi d square. Okay, and this d square is that luminosity distance that we are talking. Now to get the magnitude from this flux, what you have to do is minus 2.5 log to the base 10. Okay, and then I will use it as the natural logarithm. This log to the base 10. the flux divided by some F0, some 0 point flux. So that is how astronomers define magnitudes. Okay. So flux compared to some zero or some normal flux. Okay. That is what typically in the early days people used to compare the brightness of one star compared to some other star. And if it is equally bright, then it has the same magnitude. If it is 10 times fainter, then it's something else and so on. 100 times fainter, then 5 magnitude difference is what is how this scale is defined. Okay. So this m is minus 2.5. That's why this is minus 2.5 flux. 100 times different will give a 5 magnitude difference. F by F0, if there is 100, then log of 100 will be 2. 2 times 2.5 is 5. So that's how it is. So remember this because we will have magnitudes which are given rather than fluxes. So whenever you want to go from magnitude to this luminosity distance, you have to go via this equation. Now, okay, then how do you get the luminosity of a galaxy from the magnitude? Okay, so let's try to work that through. So this is the flux formula which is written on top, L divided by 4 pi dl square. So I told you that the luminosity of an object and the flux of an object is related to that per unit time per unit area, right? That is involved. So in order to get the luminosity, if I told you I am at a fixed distance, then whatever flux I measure can be related to the luminosity, right? If I tell you I am going to measure a flux at some standard distance and what that flux is, then you should be able to tell what the actual energy per unit time emitted is. Okay. So astronomers, when they measure magnitudes, they also measure something called absolute magnitude of the galaxy. And this absolute magnitude is the flux that you will get, or the magnitude that you will get, if that object was 10 parsecs away from. So that's how this is defined. So if that is the case, then how will it look like? So small n, this apparent magnitude, will be minus 2.5 log f by f naught. But the absolute magnitude, which is related to the total luminosity, that will be the same thing, but the flux at 10 parsecs. That I was supposed to do. So from the apparent magnitude, if I want to get the absolute magnitude, I can just subtract these two things. What do I get then? M minus n minus 2.5 common, and then log of this minus log of this. So when I subtract two logs, the arguments have to take a ratio. Right? So if I take the ratio, what will happen is f0 will cancel out. So all that you will get is at 10 parsecs divided by f. Now, if you get f 10 parsecs divided by f, and f is related to L by 4 pi dl square, then the ratio of f 10 parsecs by f will be related to dl to 10 parsecs. So that is what is shown here, dl to 10 parsecs. But there was a square here, so that 2 comes out and then this minus 2.5 becomes minus 5. So apparent magnitude and absolute magnitude is related to the luminosity. They are, yes, so they are related by this equation. I should keep this somewhere. Yeah. Okay. So they are related by this 5 log dl. Now, if you look at galaxies from gamma, we will download this and I will help you with this plot. What it will look like is this. Okay, so I'm plotting the apparent magnitude versus the redshift of galaxies. What you will see is this is redshift and this is apparent magnitude. You will see some behavior like this. So what it's showing you is that you see all these galaxies, most of these galaxies are below 19.8. And what this is telling you is that the flux of these galaxies, there is a minimum flux out to which you can detect these galaxies. The reason why this is because if you take this object, that galaxy, and you observe it for a limited amount of time, Fainter galaxies you won't be able to see. Only the brightest of these galaxies you can see. We only integrate for a given amount of time. And so there will be some galaxies which will be the faintest that you can observe in that particular amount of time. And so that is what sets this limit. And for gamma, this limit is about 1928. There will still be some galaxies which are a little bit fainter because they observed a little bit deeper, or they took spectra from some other surveys and put that in the survey. So this is the reason sometimes you may see some outliers, but we will cut them off. And this kind of graph how to get, we will see. Is that fine? Then gamma was not done in only one particular area. We had multiple different areas. We will only focus on areas which are near the equator, okay, and in the equatorial region. So there are 3 patches that you will observe. One of this patch is goes down to this limiting magnitude. There are other patches which are a little bit shallower. And so if you also plot all of these patches, then what will happen is sometimes you will see a horizontal line here, there will be another horizontal line somewhere else, and so on. So as soon as you see that, you know something is wrong, something is homogeneous, and so on. So you need to take a look at the data to understand what exactly is happening. We'll learn that when we do the next one. So that's one thing. Then what we can do is we can convert our apparent magnitude to absolute magnitude. Apparent magnitude is related to actual flux, absolute magnitude to the actual luminosity of the galaxy, right? And the difference between the two is related to the luminosity distance. So if you know the redshift, if you know the cosmological model, you can get the luminosity distance. So we will get these luminosity distances and calculate what the absolute magnitude. Now there are 2 different problems that happen. One is that when the light from that galaxy reaches us, it is also traveling through the Milky Way. And Milky Way has a lot of dust. So in between us and the galaxy, there will be this dust field. And so what will happen is the light from that galaxy is going to get reddened. And it is also going to get scattered because of this dust. And so when it gets reddened, what you need to do is you need to account for this extinction. So depending upon on the sky where this galaxy was, there will be some amount of dust and you need to correct for that extinction. So those extinction corrections are also given already in the Gamma survey data. So we will use them and correct things. That's one. The second thing is, if you have a spectrum, I have told you that all the photons by the time you observe them, they get redshift. So let's suppose you have a galaxy. This galaxy has many stars. Each of these stars has some spectrum. Then what will happen is, check this. Yeah, the audio is on. Right. By the time the light from those stars is reaching you, from the stars within that galaxy is reaching you, all of that spectrum is going to redshift. So what happens is when we observe your spectrum, you are going to disperse the wavelength. The wavelength will be the wavelength of the photons after their redshift. But the entire spectrum is going to redshift. So when you are measuring the luminosity of a galaxy, you will measure it in a particular band, wavelength band, from say lambda min to lambda max. But now think about 2 galaxies. One is at a smaller redshift, one is at a higher redshift. Both are exactly the same galaxies. But because the spectrum has redshifted, in the band that you observe, you will see a different flux pattern. Or a different luminosity you will infer from it. And that's not what we want. So what people do is they try to correct these band passes to the same exact location so that you are sampling in the rest frame of the galaxy the same wavelength reaches. That is something which is called a K correction. So we will try to do that. Again, something which is a technical detail, but you need to know about it and it's given in the data set, so we'll use that as well. So do you understand this? So there is some band in which you observe. If it was the same galaxy, you would have corrected for the luminosity distance, you would still not have gotten the same luminosity just because of this band shifting. So those bands are adjusted in order to measure what is the luminosity and compare both these galaxies with this on the same footing. So that's what it is. That's something that we will have to keep an eye on. So then I told you that all we have to do is actually count galaxies, but because of this behavior, uh, that there is a particular flux limit out to which you can see galaxies. In the absolute magnitude versus redshift plane, what is going to happen is you can't see galaxies which are fainter. So fainter galaxies are down here, brighter galaxies are up here. Fainter galaxies you cannot see at higher redshifts. Why? Because their fluxes go down, right? And so if you have a certain flux limit, you can only observe the brighter galaxies out to higher redshifts. And fainter galaxies you can only observe out to smaller redshifts. That's what you are seeing. So this particular line that is there, this particular line here, which is like an envelope, that is related to how the luminosity distance changes as a function of redshift. And what is the actual absolute, the flux limit of this survey? What is the limiting magnitude down to which galaxies have been observed by gamma? That 19.8 number that I told you about. That is what determines what this envelope is going to look like. So now think about, you have seen all these galaxies. I told you have to make a histogram. You need to count how many galaxies per unit volume take your output. Counting galaxies is simple because I have the magnitude, absolute magnitude. That will tell me what the luminosity is. So I'm done. I can count 10 galaxies of this luminosity, 15 of that, 100 of that. That is easy to count. The problem comes in the volume. So what volume do I use in order to divide that what is the number density, in order to calculate what the number density? Okay, so that's where the tricky part is, because the brighter galaxies you can observe out to large distances, while the fainter galaxies you can only observe out to smaller distances. So if you make a simple histogram, then it will look very odd. It will not actually tell you what the number density of galaxies as a function of luminosity is. One thing, stupid thing that you can think about of doing is count these galaxies, make a histogram, and divide it by some average number, average redshift or something, calculate a volume out to that redshift and get the number out. But if you do that, what will happen is these galaxies you will overestimate the volume for the low luminosity galaxies. For the high luminosity galaxies, you will underestimate the volume. So you will skew up the luminosity. That's not what we want. So we'll have to do something about this. So typically what people do are two different methods. So one is the following. Let's suppose I want to measure the luminosity function of all galaxies above some absolute magnitude. Let's suppose above is brighter than this absolute magnitude, let's suppose. Then, and these are negative numbers, so it goes the other way around. Us stupid astronomers for this, okay? But brighter objects, okay? Then what I can do is for all of these objects, I know that if I go out to this redshift, then I would have always seen those objects. So I can find out for that part what is the maximum redshift out to which I can observe all the galaxies, and then draw a redshift cut like this. So a redshift cut like this and a magnitude cut like this. All these galaxies if I use, now I know that any of these galaxies will not be missing, because whatever this galaxy is, anything which is above will always be seen out to redshift of what, 0.25 or 0.24 here. So if I use only the galaxies within this volume, then it's not a problem. I can make a simple histogram, divide by the volume, out to redshift 0.25, and I'm done. Okay. Then I can get the luminosity function. Now, how many galaxies per unit volume of a particular luminosity I should be able to get from. Is that okay? Yes, no? It's too fast. Okay, let me do it again. Okay. What I want to measure is, see, these numbers are absolute magnitude. These are luminosities of galaxies, energy per unit time. Okay. In principle, it's actually the flux, but flux at a standard distance. So I can always convert it into a luminosity. This is related to the luminosity of the galaxy. So anything horizontal is the luminosity, same luminosity galaxy. And so this same luminosity galaxy, if I'm asking, can I see them all the way out to say 0.25, where I'm going to put a point? No, I can. Anything brighter, I will still be able to see out to point. No problem. I do see things, galaxies here, but I'm going to ignore them. I'll just throw them out. Because if I go out to this volume, I won't be able to see the fainter galaxies. So then I cannot do a simple step. So I'm going to remove them out. I'm just going to consider this square and make that histogram divided by the volume and done. But you will say that, look, I'm throwing so much data. Data is very expensive to collect. So you should try to use as much data as possible. So you can adopt the approach that you will not leave any galaxy behind. So if you adopt that approach, then you have to be careful. Because now you have to say each galaxy, you see, you can observe it out to a certain distance, a certain volume. Okay? So what you do is you make a histogram, but you weight each galaxy by 1 over the volume out to which you can see. If you do that, you automatically get the number. Okay? So this may sound strange, so let me again tell you. Let's look at this. Okay, let's take a small slice here between this magenta line and maybe the width of this magenta line. Right? All the galaxies that are there within that small width are galaxies which can be seen out to this redshift. So what I can do is I can count those galaxies and divide by the volume out to which I can see those galaxies. I get the number. Yeah. And I repeat it for that luminosity being a little bit above, a little bit above. So I make many luminosity waves and I can do this exercise. So this maximum redshift out to which you can see it is called, the maximum volume out to which you can see this galaxy is called Vmax. Okay, and Vmax in a flat universe, the volume out to redshift z is 4 pi by 3 times the moving distance cubed, right? So in this case, instead of 4 pi, we will use the area of the survey of gamma. Because gamma is not seen over all sky, it has only seen some region. So we'll use only that particular region. We'll plug that in here, whatever is the area in radians, steradians, that we put down here. If it was full sky, it will be 4 pi, just like this. But it's not full sky, so this omega by 3 into this psi cube. And this psi cube depends upon the luminosity or the absolute magnitude of your galaxy. So we use this as the weight in order to compute this luminosity. So this is where we are going to. So I think I introduced all the terms that we are going to need in the tutorial. So one last thing that I wanted to show you is how this function is going to look like. So it will look something like this. So if you plot the absolute magnitude such that brighter galaxies are on this side and fainter galaxies are on this side, I have purposefully flipped it because I want brighter on this side. That's what you are used to. And then this is number density axis. So you will see something which looks like this. Lots of faint galaxies, very few bright galaxies. So this is the kind of function that we should be able to see when we compute this luminosity. So typically people parameterize it with this kind of a form where phi L dl is the number density of galaxies between L to L plus dl. And that function, it looks like this. Phi star by L star, L by L star to the alpha and exponential. So there is a power law behavior at faint time. This does not matter when L is extremely small compared to L star. So then the exponential is exponential of 0. So this goes away. So this tells you the power law at the faint time. And then the exponential function comes into play when L is really large. Okay, so this L star is called the knee of the Schechter function. You change L star, it moves up and down here like this. Sorry, left and right here. If you change alpha, it changes things here at the faint time. Okay. And if you change phi star, then it moves up and down. So the whole curve goes up and down. So This is typically how people characterize this luminosity function and these parameters with which people parameterize the luminosity. So similar to the luminosity function, I don't need this. There is something called a halo mass function as well. So in the universe, there is a lot of dark matter in the universe, and this dark matter comes into virialized clumps of matter called halos. And these dark matter halos, they have a certain mass. If you look at the abundance of these halos as a function of mass from numerical simulations, then they also look like this. So there's an exponential drop and a power of the halo. This is not a coincidence that the luminosity function also looks like this. This is because galaxies live in dark matter halos, and the bigger the dark matter halo, bigger is your galaxy. And so more luminous halos, more luminous galaxies live in more massive halos. More massive halos are less abundant, exponentially suppressed. So the number density of galaxies will also exponentially suppressed. And so inter-galaxies, you will see a power curve. So you can use this halo mass function predictions from simulations and the observed luminosity function to figure out what is the connection between galaxies of a particular luminosity and halos of a particular mass. That's called a galaxy dark matter connection. And so people work on this and they have plots like this where it is stellar mass or luminosity of galaxies as a function of halo mass, and it looks something like this. So if you get some time later on, try to do this kind of matching and figure out what this function looks like. But that will be for homework. Today we will just do luminosity. Okay, that's it. So the lecture part, I'm done. So now we'll take some questions and then immediately do the tutorial. No. That is different. Yeah. So that the K parallel, K perpendicular that you're talking about is related to the peculiar velocity. This is not related to peculiar velocity. Just because there is a cosmological redshift, the spectrum itself shifts. And so the observed band is a particular observed wavelength band. And so you sample a different energy, a different rest frame spectrum for galaxies which are at different redshifts. So that is what it tries to account for. It's not the same thing.
Last part, luminosity and halo mass function, how you relate that?
Yes, so abundance helps you to relate, right? So the reason why I told you, the reason why high luminosity galaxies are exponentially less in number is because dark matter halos of very high mass are also less in number. Why that happens, it will take long time for me to explain. I mean, I have those in my slides, so I try to prepare even that, but time-wise, I don't think we'll be able to. So if you can match the number density of galaxies to the number density of halos, then you can also get the connection between the mass and the luminosity, because the number density, they're all related, so that's fine. Okay. Okay, good. So now let's try to get to the hands-on session. I have a Python notebook and I will share the link with you also later on.
So you can put it on the WhatsApp group.
I will put it on the WhatsApp. I will take a chair. Now I can see. Right. Right. Okay. So let's see. Okay, what I'm going to do is I'm going to send this Python notebook. And then I will also load it on the screen. Okay, let me share my screen. Is it easy to read or not?
They suit it. That's it.
Yeah. Okay. I shared it on
Oh, yeah, I just.
Okay, let me know once you have downloaded this notebook. I try to work on this very quickly at the end.
And it will give me this understanding.
No
So
problem.
you can your presentation.
Yes.
Some people are getting kind of this, so that's what.
Yes.
They want to know.
Yes. I have written it in the slides. Okay, so we have about an hour or so to finish this, okay? I'm supposing that this will be done quickly, but let's see. And Priya, are the Zoom participants also in the WhatsApp group? Or-
No.
So should I send them the?
Yeah.
Okay.
Then there's 600, no, the through many. I don't think WhatsApp allows 600. This is only the offline. You can give them.
Okay, I am going to send the file to the WhatsApp participants as well.
WhatsApp has Zoom.
Sorry, Zoom participants.
Internet नहीं आता। ये सब चल रहा है। हाँ। अच्छा ये YouTube चल रहा है।
Okay, can someone in the chat let me know that you have received this link? That it works. Okay, very good. Thank you. Okay, how many people have managed to download? 4, 5, 6. Okay. Okay, many are remaining. So can you please help your friends? That is usually the best approach because it's a scalable approach. There are so many around you. Just please help them. If you have USBs, you can share it with them. Okay, what we'll do is I'll give you another 5 minutes, and within those 5 minutes, make sure you get help from someone who has already done it, or then otherwise you have to listen to me only. Okay.
Luminosity of this and theoretical
Yes, yes, I was going to cover that, but because I didn't know the exact background that everyone will have been, then I decided to go even for lowest common denominator thing. But I have it in my slides, so if you want to take a look at it. Yeah, I will share the slides. My lecture notes also have many of these things, so those will also be shared.
Just put this thing. In fact, how many of you have never used Python before? Everybody knows. The word is not.
There is one girl, no, who did not have it, who had not used. I don't know why. But anyway, you will sit with someone, so then it's okay. चल नहीं रहा है इंटरनेट नहीं चल रहा है It's connected.
This is where you know how it's done. It's not it's not it's it's done. It's not it's that's fine, ले लो. Self-sufficient बनो अपने. Big man होगा.
You can't movie नहीं download करना
It's working. You say it's on. This is coming to
Yes, yes, yes. This is good. No, but it's quite a few hundreds of megabytes of files that you need to download. Okay, yes. Not working? Yeah. Huh? LaTeX distribution. You can comment out one line, I will tell you which one. Oh. You should look at him. Oh, you are also in the same category. No, you know. Please look, because starting from here, it will take a long time for me to explain. And you should always learn from each other. Okay, then it will work. Me going to everyone will not work. How to get to this point, you will learn today, tonight, or something. Okay, good. So I think we should start because otherwise we will get late. So this Jupyter notebook, I have opened gamma_LF. This is what I had sent you. So as I said, the luminosity function from the gamma survey is what we are going to do. This is the number density of galaxies as a function of luminosity and quantify the abundance of galaxies. This is expected to follow this halo mass function, modulo the connection between the dark matter halo masses and the galaxy luminosity. And then the gamma survey is the spectroscopic survey of galaxies, which targeted galaxies from the slow digital sky survey. And compared to the spectroscopic component of SDSM, gamma is deeper, but it covers a much smaller portion. So we will compute the luminosity function using this. So if you look at the first cell, it just imports phyla as PL. Then we will make inline plots. So that's why there is the second line percentage phyla inline. Some of you may not have LaTeX. Okay, LaTeX installed. In that case, please comment out this line. Comment text dot use set equal to. Actually, these last three lines in the conf you can comment out if you don't have LaTeX. Okay. So this is just related to the PNP files that it will generate and the quality of the figures that it will generate. The more DPI you give, it takes longer to render, but it looks more beautiful. It will have a higher resolution. So DPI is dots per inch. Dots per square inch. Okay. So these last three lines have to be commented if you don't have LaTeX. Otherwise, the plots look more publication quality if you have the last three things. Width is equal to 600, otherwise it will have generated smaller plots. So that's why I also set up the width. And then I reload this config file so that the plots will look nice. That's all I'm doing in the first step. Okay. Nothing about gamma yet. Then I needed to import quite a few libraries automatically. So first is the files that gamma gives are in terms of fits files. These are fits tables files. So to read them, you need to have this first line from ascii.io input fits. Pandas gives you different kinds of functionalities in order to merge data files and so on. So that's why there are multiple files in which the data is distributed. You will have to merge it together. So that's why you need pandas. Then you will need numerical Python libraries. So import numpy as np. And then in order to do the cosmology calculations, you have this AstroPy library, so AstroPy.cosmology, and in which it has this flat lambda CDM. And then there is another function called z at value, and we will use it. I will tell you where. But flat lambda CDM is that cosmology module, which will allow you to go from redshifts to any luminosity distance or moving distance or any other distance. Okay, so the third cell, you see that I say Cosmo is equal to flat lambda CDM. Now you have to tell me which of the parameters I have to give to flat lambda CDM. We have discussed this before, right? There are two parameters which we need. Omega and H naught. Those are the two parameters that we need. Because that's what defines this flat lambda CDM. So we will pass those two parameters like this. Omega n 0 is 0.3. H naught is 100. This H naught is given as 100 because there is an uncertainty in the value of the Hubble constant right now. So what we do is we write the Hubble constant as 100 times the small h. So you pass everything in H naught of 100, then the distances will be in H inverse megapascal. So all our distances will be in H inverse megapascal because of this. Okay. Okay, so now what we'll do is first understand how to use this cosmology module. Okay, so let's plot some of these distances that are there. So let's create a Z array which goes from redshift 0 to say 0.4, and there are 1,000 points. So np.link space from minimum redshift to maximum redshift and how many points you want. So this creates an array starting from 0 to 0.4 and with 1,000 bits. That's that line. Then chi of z is basically the moving distance in this cosmology module. So chi of z is cosmo dot moving distance. And this moving distance is a function of redshift. So I have to pass the redshift. So I give the array, and it should give me back in that. Okay. So this is the function chi, moving coordinates. Then there will be luminosity distance of z. So instead of moving underscore distance, there is a function called luminosity underscore distance. So that is the function that we call with redshift array. And it gives me dl of z. Okay. Then you will also require volume as a function of redshift z. This is because we want to calculate the number density. So we'll need a volume at certain point. And so cosmo.moving volume, moving underscore volume of zr gives the volume over the entirety of the sky. So this is how you get the moving underscore volume. Now, if gamma is only certain steradians, not the full entirety of the sky, then what you will have to do? You will have to divide this moving volume by 4 pi and multiply by the steradians, and then you get the volume of the cell, outer redshift cell. Okay, so now that we have calculated these cosmological quantities, you can make plots. So let's make a plot of chi as a function of z, or luminosity distance as a function of z, that is shown in the cell number 5. And so if you run it, you will get a plot like this. It shows distance as a function of redshift, and I have plotted two different distances. One is luminosity distance, The other one is this moving distance. And you can see that they behave in two different manners. Yeah. Both of them increase as a function of redshift Z, but one of them grows faster. Now, does someone remember what may be the relation between these two? Right, so there was a f of I divided by 1 plus z and f of I multiplied by 1 plus z. The luminosity distance is more than the going distance, so it is multiplied by 1 plus z. And so what you can do is, as an exercise right now, if you want, you can check, is the ratio of dn of z and chi of z equal to 1 plus? Can you do that quickly for me? Okay, just check what is the ratio of dl of z versus chi of z. No, it is co-moving distance, so it will be 1 plus z. If it is 1 plus z square, I did some mistakes of that. Just check. It looks like 1 plus z because see, when the moving distance is 1000, I get 1400 for the velocity. So it's not square. It is, otherwise it would have been 1.61, 1600 or so. Okay, so is everyone with me so far? Moving distance of z is that blue line. Luminosity distance is the orange line. And what did I ask you? To check that the ratio of chi of z by dl of z is the same as the redshift. Okay, so if I do a print 1 plus z r, that will give me what is the 1 plus redshifts. Okay, and there are 1000 points, so it is very difficult to see them. No, not just the mean, but we will check one by one, right? And then what I want is also the ratio of this, right? So dl of z divided by chi of z. Okay, let's check 1.0004000. So there's a none that is expected, but then 0 by 0, that's right. But otherwise, you have 1.0004004. So all these numbers should match. Okay, so what I can do is I can ask what is the NP dot sum of 1 plus z r equal to dl of z. But this nan will not work. I'm not allowed to do this. Nan sum. Does nan sum work? No. Well, let's plot it. Maybe that is better. So AX dot plot. This thing. Okay, so you see 1 is to 1 line. 1 plus z is on the x-axis, and the ratio of these two numbers is on the y-axis. It starts at 1, 1, and it goes to 1.4, 1.4. Okay? Yes, no? Okay, so let me see how far we have got. Okay. Did everyone manage to calculate those moving distance, luminosity distance, V of Z? How many could do that? Zero. Okay, one. Please.
Does it actually?
Okay, so what I'm going to do is I'm going to go around and check what is happening. Okay. Yes, two. Very good. You need help or you are done? Oh, Priya. She's following. Oh. Ah, you can read that. Oh, start. I cannot come out to raise speakers. I think they are the ones.
Limited, right?
Yes.
So you can't approach any of the speakers.
That's what.
That's strange, but that column line is best to be used.
Yeah. But can you take a look who people are able to do it or not? So if you don't have libraries, Astropy or Pandas or something, then you need to install them, okay? Otherwise, again, it won't work. So you first install them and then you restart your Jupyter notebook. Then it will work. Otherwise, it won't. What is not working?
Because laptop, you see, not the laptop is supposed to be asking, then what is the way?
It's working? Okay, it's working. One more working. So give me a thumbs up if it's working. And also people in the chat, please send whether things are working for you. Let's see. Please resend the notebook again. Okay. Someone said it. I see. Yes. What I will do is for a few minutes, I will just roam around and help you guys, okay? I will be away from the mic for some time. Yes. How it works?
That's the yes.
It depends. It's not really. I think we must have taken that. That's why though. That's the
Yeah, market में आप लोग की ग्रुप में मैंने 5 लोगों को डाल दिया लेकिन काफी आपको व्हाट्सएप ग्रुप पे मैंने डाले 5 लोग आपको शेयर
How many people want? That's all it's. Fine, it will take time. Huh? Appearance is the key here. So we could manage easily. Very good. Very good. What is something? I'm not from.
Some of them don't have alpha inside. You've got that.
And then not. Okay.
I can't move my head, they also already did.
Yeah. Don't worry, we have to be answers. Okay. Okay, so. Okay, so I think we are mostly, at least people have gotten the plot for chi of Z and dA of Z. So now that you have it, you can check that the ratio is exactly 1 plus Z. Okay, so that was the exercise. Then if you plot the redshift versus the volume of Z, now typically people define volumes in megaparsec cube kind of units. And so here we will try to plot it as function of gigaparsec cube. Otherwise, these numbers become too large. You have to pass it to the max. Okay, so I'm plotting ZR, comma B of Z divided by 1E9. And the label is going to be for the volume. So you see how it looks. Okay. It's basically like pi cube, and that's why it has this cubic kind of behavior. Okay. Then another exercise for you to make sure that I of Z and the volume are exactly related by this factor. Make sure that that is the case. Okay, so now let's come to galaxy catalogs from Gamma survey. So there are 4 different catalogs that you need to download. So please click on those links. Those are 100 megabytes, sometimes different sizes. So please download all those files. The input catalog, it tells you what is the photometry of the galaxy. So what is the flux coming from this galaxy? Those are listed in tab K. K corrections, here's this K correction that I told you about to deal with the fact that the spectrum of a galaxy redshift. Then the spectral file, it has the spectroscopic redshift of the galaxies that have been observed. And extinction tells you what is the extinction of the dust, how much of the light it has absorbed. That is what the extinction correction will tell you. Okay. So all these files you need to download. So once you download these files, you will have to use AstroFile's table in order to read these files. So what you do is from AstroFile.table import capital table. And then you open the fits file and ask AstroFile to read the table, read the data from that file into a table, and you convert that table to pandas data frame. So now input called cat A will have different columns. Then similarly, you read the other files, spec call and K correction and the extinction file. All of these files you read one after the other and convert it into pandas. So you will see these columns, spec columns, it has spectroscopic ID from which survey it came from, what is the code of the survey, the RA depth, which is the position on the sky, W being W max, Z is redshift, and Q is some kind of quality flag, probability of the thing to be the best. So all of these columns are defined in the Gamma website. Okay, so if you go to Gamma website, I will put the link to this website as well. You go to schema browser, and then it gives you this equatorial input catalog. And the input catalog A, yeah, it's 200 megabytes or so. So it will tell you what is the meaning of each of these columns. Okay. So RA means the coordinate, equatorial RA coordinate, equatorial depth coordinate. Then the flags, primary targeting type, whether it's a galaxy or a star or some sky fiber. And then what is the PSF magnitude, what is the fiber magnitude, all of these magnitudes are also listed. Okay. I have not told you what is the PSF magnitude, what is the fiber magnitude. What we are going to use is this spectro magnitude underscore R. Okay. So there is a R band filter. In this R band, there is something called a Petrosian magnitude. That's the one that we use.
Now the net is working fine. No, you take it complete.
Okay, so spec all the columns, input catalog A, K correction, extinction, all of these columns you can check what you get. Okay. So now what I want to do is the input catalog that is there. See what this gamma survey has done is that even if there is one galaxy, it has taken spectra multiple times sometimes. Okay, and one of these spectra will be good or the best out of all these spectra. So you don't need to keep all these copies of all these different spectra that are there. You can only use the best spectrum copy. So in order to do that, this is what I've done. Well, first what I've done is I've made sure that the catalog has site equal to 3, because site equal to 3 is galaxies. Okay. So that we make sure. And so we only use site equal to 3. And you reset the index so that the pandas data frame will only keep those rows which have this site equal to 3. Okay, in addition to this, what you can do is for I equal to 3, that is fine. Yeah. Okay, then what we have to do is you will see that all these columns they have a particular column name. It's called kata ID. Okay, so this is the catalog ID in Java. And this is a primary key. So for all of these files, you will have one kata ID. So what we are going to do is we are going to merge all these files into one single data frame with using the kata ID. And that is done with this particular command. So I will say gamma is equal to, there is something called reduce, which takes in a function and it merges two different pandas files. Okay, so left and right. And this has to be run on all these different files, catalog, input catalog, ACOR and extension. So when you do that, you now get a combined catalog with all these different columns. Okay. So now that you have everything, now you can start to visualize what that catalog looks like. So one thing, for example, that you can do is you can maybe create another cell here, and you can try to plot the array and deck values, okay, for all of these. So let's create a AX, this pld.subplot111, and then we will do a scatter plot of all the gamma galaxies, and we will plot the arrays and the deck. Okay. So when you do that, you will see that there are three different fields that gamma has observed. Okay. So array between some 120 to 145 and declination between -2 and 3. Then there is another one which is centered around 180, declination between -3 and 2. And then another one from 210 to 30 or something, and declination between -2 and 3. Okay. So there are these three different array decks. So if you go to the Gamma website, you can see that that is indeed the case. So Gamma data release 4. You can see all these different fields. Okay. They have a array range and a deck range. So you can figure out which of these fields we are looking at. So these are equatorial fields, the fields near declination of 0. So these G0, 9, 12, and 15. I think these are the three fields that we are looking at. And they have an area which is given of 60 square degrees each. So these are the fields that we will take a look at. Or we are looking at. Okay. Now the files that I downloaded, it seems that just by looking at it, you can say that, see that the third field has a higher number density of galaxies than these other two fields. And so the magnitude limit must be different in this field compared to these two other fields. So you can try to verify that. So how will we verify that? We can verify that by plotting the apparent magnitude as a function of redshift. Okay, so if I do X dot scatter, I take the redshift values, which is gamma dot capital redshift Z values, and then gamma dot say spectromag underscore R dot values. So if I plot that, you will see a function. Okay, that's great. Let's see. Let's go to 0. Yeah, so it looks very odd like this, but we have to always go down to the right limits and then it will become clearer. So we set the limits, say 0 to 0.4. Some of these objects are stars, that were these negative redshifts. So don't worry about them. Then y limit we can put from something like 16 to 21. Then you see things like this. So you can see that somewhere you have this absolute magnitude threshold, which is here, and then another one which is absolute magnitude, sorry, apparent magnitude threshold, which is here, right? So one is 19.8, the other one is 19. So I guess not all of the galaxies have been made public, and that's the reason why you see two different limiting magnitudes. So what we are going to do is, we are going to restrict ourselves to the field which had the highest number density. And so it must have gone deepest. And so we will go down to 19.8 by looking at all galaxies above 200. Okay, so RA beyond 200 is what you need to do. So we apply these constant data. So in the constant data, what I'm doing is, I'm demanding that my RA should be greater than 200. And I also demand that my magnitude values corrected for the extinction, they should be brighter than 19.8. And then I'm going to apply this IDX when I make the plot. So I plot the redshift versus the extinction corrected magnitude. And only those which satisfy this above criteria. And when I do that, then I can see that I get the plot that I've shown in the slides, which is apparent magnitude versus redshift. Only up to 19.8 you can see things. Beyond that, fainter galaxies you can't see, brighter galaxies you see. So now that we have this, we can now make the absolute magnitude for these galaxies. Okay, so only for these galaxies we will calculate the absolute magnitude. So that absolute magnitude is the apparent magnitude minus the extinction. So correcting for the extinction minus the K correction. So those we will leave. Okay. But then the thing that we learned that the absolute magnitude minus the apparent magnitude, that is related by 5 times the log 10 of the luminosity distance. So that's what is shown here. The luminosity distance is calculated in megaparsecs, and that's why we want a factor of 10 parsecs to megaparsecs. So that is a factor of 5. 5 times 5 gives 25, so that's why there is an extra minus 25. That's all. So 10 parsecs to megaparsecs is a factor of 10 to the 5. So that's the reason there is a minus 25. So this is how you can calculate the absolute magnitude of galaxy. And then you can make a scatter plot of this from the sky. So what is the redshift versus the absolute magnitude? Now remember, this absolute magnitude is giving you the luminosity of galaxies. So brighter galaxies are below, fainter are above. Sorry, the opposite way here. Brighter are above, fainter are below. So that's why I've inverted the scale here. It goes from minus 15 to minus 22. It's inverted scale. And now you can see the fainter galaxies are missing, brighter galaxies are only the side. So once you have this, now what you want to do is for every absolute magnitude, you want to compute what is that Vmax. What is the maximum volume up to which you can see a galaxy? Now this is a little bit more involved. So let's try to understand how to calculate this. So first you define an array over which you will measure the luminosity function. So I'm defining from minus 15 to minus 23, and I will do it in 100 data points. I have a limiting magnitude which is 19.8. So I'm calculating maximum luminosity distance out to which I can observe this galaxy, given that the magnitude limit is this. So capital M is small n minus phi of dl minus 25. So phi of dl will be small n minus capital M minus 25. So if I put this as the magnitude limit, this minus, this 19.8 as the magnitude limit, I subtract this absolute magnitude, subtract another 25, divide by 5, and then do a 10 raised to that number. Then I should get the maximum luminosity distance out to which I can see the galaxy of particular absolute magnitude. So that is the DL max that I'm trying to get. And once I have the maximum luminosity distance out to which I can get this object, I need to figure out what is the volume. So first I need to calculate the redshift out to that DL max. And so I need to do an inverse function. So this is that inverse function. What is the redshift at value? What is the function? The luminosity distance function. And I need to give this DL max in units of megaparsecs. So that's what I've done here to calculate what is the redshift. And once I have the redshift, I can calculate also what is the maximum volume. And for that, I am now using the fact that this is a 60 square degree survey. 1 square degree is np.pi divided by 180 the whole square steradians. And so 60 square degrees will be that many steradians. So that many steradians divided by 3 multiplied by this moving distance z max cube. So this is the formula which was written in the slides, omega by 3 divided by pi cube. So now that I have the Vmax, this Vmax is related to the absolute magnitude. But I need to calculate this for each and every galaxy. So what I will do is I will put that on the spline. Okay, I will put the absolute magnitude versus volume on a spline. So that for every galaxy which has a certain absolute magnitude, I will pass that absolute magnitude and it will give me the maximum volume out to which I can see it. And so that's why I have made this line. And after this is just making a histogram, that's it. So we have some bits in which we want to compute the counting of galaxies. So I make a histogram of this absolute magnitudes. As weights, I give this 1 over Vmax. But I also have to give a difference in the binning, right? Because you have to give per magnitude bin how many number of galaxies are there. And so I have also specified this bin depth. And I give the bins, what these bins should be. And I plot it as a histogram. And when I do that, I actually get the luminosity function of this galaxy. So if you look at the gamma luminosity function that people have previously measured, so this is here. So this is from another survey, SDSS. You can see that it also goes down to 10 to the minus 2 or so at minus 20. And so our function also goes to 10 to the minus 2 roughly at minus 20. So it's basically the same. And it continues down to 10 to the minus 1. And that's what we see in this function as well. Here. So it's at 10 to the minus 2 and it keeps on moving up and up and up with some power law, it will reach minus 1. But slope was less fainter than gamma. And so it peters out at minus 20. Let's look at our gamma. Oh, sorry. Gamma is going down to minus 16 as well. So slope you could have seen out to this. And it looks like a power law with an exponential cutoff. When you go further inside, or further fainter, you see that there is another power law that we see. So this power law is changing. Maybe it's becoming a double power law or something. So all these things you can learn by looking at the galaxy luminosity. Yeah, so this is an interesting phenomenon that the slope changes. And this has to do with the fact that the luminosity to mass relation, it does not look like a power law. It is also like a broken power law. So let me show you this. So here, If you look at this relation between luminosity and halo mass or stellar mass and halo mass, you will see that it is not a single power law, it is a broken power law. And so in this broken power law, there is also a small shift that happens at low redshift. And so that is the one which is causing that upturn. So these are things that as you go to do more and more research into this, you will start to see these things come up. Okay. And this has to do with what is the efficiency of star formation in halos of mass and how it changes and how do star formation, how it creates feedback and affects the luminosities of galaxies that forms in it. So it's a lot more involved, the answer to that question. Yes, so if you look at the luminosity versus halo mass, you will see that 10 to the 12 is where galaxy formation is most efficient. And if you go further below, then you don't see many galaxies forming. And so that efficiency is what is shown in the right hand plot. But of course, we don't have time to go into this right now. Okay, so that was a long-winded way to get to a simple thing, which is measuring and counting these galaxies. But you can see how much knowledge is involved behind actually computing these luminosity functions. Even though it's a simple counting business, you need to know the volumes, you need to understand what those volumes mean. You need to understand that all the galaxies, you don't see them because of the limitations of your survey. And after you do that, then you can get at the true luminosity function of galaxy. So that's about it. That's what I wanted to cover. So in the last 5 minutes, if you have any questions, and I can go around and see that, make sure that you have at least reached the point that I wanted to reach. Thank you.
Thanks, Surhud, for a lovely session. Any past questions? Yeah.
Maybe the first lecture, like what happens, like you said that Phaser is not like square, that turns out that the universe is accelerating. What happens? That's the real things.
Oh, if the universe is decelerating, so depending upon the constituents of the universe. So let's suppose that you only have matter in the universe. And depending upon the amount of matter that you have is greater than the critical density or less than the critical density, that will determine the fate of the universe. Okay? So if you open my lecture notes, then I have these things properly coded up, so I will show you. So this is scale factor as a function of time, and in 3 different universes. One is a flat universe, that's the red line. Okay, we are here today, scale factor is 1, and t is 0, let's say. You go in the negative, that is the earlier times. You go in the future, that is positive times. Then what you see is that if you are in a flat universe, you will continue to grow and you will keep on growing. And this scale factor, asymptotically, it becomes flat. It will reach some kind of a maximum value at infinity. If you have less density than critical, then you continue to expand and you keep on expanding forever. And your speed with which you are expanding, it does not saturate, it does not go down to 0. It just keeps on going at some speed. And if you have more matter than the critical density, then you reach a maximum, and after that maximum, you start to collapse. So these are the things that you get. Now, these are 3 different kinds of universes that you may live in if you only have matter. But if you have a omega lambda, which is this dark energy, then this becomes an exponential this. So it becomes really fast exponential expansion at that point. Radiation, but radiation does not matter for this behavior because it just dilutes off. It matters only here, extremely low values of state factor here or here. But other than that, even if there was a little bit of radiation, it was fine. The problem is because of Tapa. That is what starts really. Okay?
Your car is ready.
Car is ready. Okay, sorry, I need to go there. Thank you. Yeah, so my suggestion will be the following. If you have more questions, maybe Priya can create a Google Doc. And in that Google Doc, you put in if you have more questions. And I'm happy to go through it.
WhatsApp group,
Yeah.
they're all in WhatsApp group.
Respond.
So they can, you can even get his number is there on the WhatsApp. Different messages.
We will send this.
Yeah, this lecture notes will be shared.
Yeah.
Slides, lecture notes, everything. will be.
What we do is on the website, we collect everybody's stuff.
Okay, thank
So
you.
thanks, thank you, so. Thank you.
Thank you.
Okay. Okay, so one small piece of good news. In the main guest house, there are 6. There are 3 rooms. So how many girls do we have in HRTC? How many girls are there? What's the girls? 1, 2, 3, 4. Only 4 girls in HRTC. Or 2 more. How many girls are in HRTC? 6. Okay, so all 6 go to the main guest house today. Okay? All 6 girls, you can accuse me of whatever you want, but 6 girls who are there from HRDC can go to the main guest house. Some people didn't turn up and all that, so the rooms are free. So you have to please take us along from there. Okay, 3 rooms in HRDC. Okay, wait. Not everything is good. Meanwhile, you'll have to install some software. Okay, so yeah, Najam. If you remember today, when Chengsui was talking about what we are going to do.
We want to
is-
go to the guest house, pick up our bags and.
Okay, by the time I'll just copy them, Priya will speak with the card.
Yeah, we take.
Yeah, by the time I'll just.
So one software you have to install is called TopCat. Okay? TopCat. So please write TopCat Bristol. Okay, it's a University of Bristol.
It's under.
This is the virtual observation software, and the person who wrote it, Mark Taylor, he will be talking to you tomorrow afternoon. Okay? So Mark Taylor is the person who actually wrote the TopCat software. See you, Ajay. Bye. Nothing. Oh, no, I don't. I'm next. Anything. Ah, okay. I think I wrote it. I can see that. Oh, that was the beginning. So, right, that's it. Thank you. Just, that's it. Najam is coming down.
Okay.
You just got to install some. So, one thing you'll have to install is TopCat. Okay. So the person who's written this software, to install it, it only needs Java. It's a Java-based software, so it doesn't make a difference whether your system has Windows, Linux, Mac, whatever you have. It's Java-based. All virtual observatory software is Java-based, so it doesn't make a difference what OS you're using. So for TopCat, you may have to install Java, okay, and after that. To TopCat, it's like Bristol, because it's from the University of Bristol. And like I told you, the person who wrote the software is called Mark Taylor. He'll be talking to us tomorrow after lunch. Okay? So please install the software. If you want, play around with it also, because he's going to talk about some stuff about that. So TopCat is one thing you're going to install. Another thing you need to install, James spoke about it today. Even Ajit spoke about it today. This is TopCat. The other thing you're going to install is Aladin. Again, I'm writing Aladin astronomy because there's another Aladin which you all know about. But you go to Aladin. Aladin is basically, so TopCat is a software which is obviously a much better version of Excel. So TopCat basically does spreadsheets. So when you have data in the form of catalogs, right? One option is you write Jupyter notebooks and do stuff with it. The other option Other option. You really manipulate the data, right? Which is in the form of catalogs. So you do it in TopCat. Typically, we do it with students who do not know Python, for example, right? But for example, people like me who do know it, we still use TopCat because you can play around with it very fast, see how is the data, and then you may want to later on write a notebook on things you've played around with, right? So TopCat anyway works out very well if you have data. You want to try something, some hard plots, you can do some plots, 2D plots, 3D plots, various things. A lot of things get done with TopCat, okay? So when I do my tutorial, I'll be using TopCat as well as Luminosity. I'll show you both. Okay. So TopCat is a very good thing to have. And like I said, then tomorrow we have a talk specially on TopCat. Prepare yourself for it. Okay. The other software which we would like to hear from you is Aladin. Aladin is a software which, like Ajit said, you have to magic lamp and the genie appears, right? In this case, what happens is you give the code and the images appear. Okay. So you'll actually go to it saying Aladin's address. Okay. There's an Aladdin Lite and there's an Aladdin desktop. You can install whichever one you want. Again, like I said, this is Java based, so it doesn't make a difference what the OS you are working on. It will work. And I can show you, for example, oh, sorry. Yeah, you open it, you'll get something like this. It's a opening. So basically what it's doing is it's an image display software. Yeah. Fine. So Aladin will basically, you will define a part of the style and it will give you an image of that area. Okay. And we'll show you how, I will show you how if you have catalog data, you can overlay it on an image. Right? So if you have various sources, you can mark them and all using this. I'll just check why is it not opening. I'll just open it again. I'm seeing this. So, okay, so this is so for example, here I write an image. I write something. I say, for example, I want M31 and wrong that. So I'll put M31. I want. Sorry, I have extra things to do. So it's fine. So you see I put M31 with here. I can actually zoom in and zoom out. Get all the things. This is the DSS image. I can override, for example, a wise image. Wise will give me an infrared. Sorry, yeah, so you can see you have planes over here. We'll show this to you properly tomorrow. But you have planes, but you can see on the right over here. This is a plane. This was the I zoomed out. That's it. This is the DSS image. This is the wise image. Sorry, this is the DSS. This is the wise image. I can even overplot other catalogs, for example, if I want to put Gaia, I want to put some bad, I can overclock by. So it will overclock like that. So this is, these are all the ISO schemes. And similarly, I can get some bad also, it's spoken about it. Yeah, so I can put Simbat, the blue message Simbat, I can select it and mark it. And it will tell me various things about Simbat. So you can see here it's telling me for each object I want, I can actually click it. It's not working now, it's taking lots of feedback. So in short, that's all. So your homework for today is to install TopCat and play with it. Acha?
Yes, sir.
You want to tell them something?
Uh,
Call the mic is there. I will say what's
So, hello, yes. Hello, just it will take a while. Hello, hello, hello.
सर ये ऑन हो गया है सर ये माइक बेस्ट ये ऑन
That should be working.
Best-
Like, he's put one more.
तो आवाज करके नहीं सही है एक मिनट सर ये ऑन हो गया है लीजिए
Ready? हो गया.
And then, has it picked up the net?
Yeah, he's put another router. One more. Nice. So ये desktop download. That's the one. That will be system admin उसके हिसाब से download. ठीक है? That's the router. ठीक है तो प्रॉब्लम कहाँ जा रही है?
Yeah, since been a long day for all of you. So, do you still have energy or you want to disperse? Yes, so, sir, basically what I want to say is you must have got a fair enough idea of what virtual observatory is. Yeah. See, there was a time when astronomy had very little data. Whatever people saw through a telescope, they either sketched it out or then things improved, they would put a camera and take a photograph. And then you got the CCTs and so on. And gradually, we have tremendous amount of data available. So astronomy has gone from a data poor science to a very data rich. So there are many ground-based telescopes, space-based telescopes, and they are collecting tremendous amount of data, petabytes of data, right? And in each frame earlier, you took a frame and you had a cluster. The instruments were not very sensitive. They would image their clusters, they would think there are 100 objects or 50 objects. Now we see that there are thousands and millions of them. So there's a tremendous amount of data which is coming in. And hence it has become important for us to use computers to sift through this data. So this virtual observatory is a set of protocols. The word they use is protocols. Protocols is nothing but a set of rules. So many astronomical observatories, ground, space, on Earth, they got together and made an alliance, and where they decided that the data has to be shared in a very specific way. So they defined protocols and rules how to share data, how to access data, how to analyze it, and so on. So to analyze it, they developed tools. For example, Priya just showed TopCat. How many of you have used TopCat earlier? 1, 2, 3. Yeah. So please go home and install TopCat. You know how to do that, right? What happened to this? Okay. Yeah. From there,
My lab, not this one.
no, this is also fine, no?
What's happening to that share?
Okay, so, you will see words like tap.
I'll give you a quote.
So basically, there's a lot of jargon which is involved, but you have to look beyond that and not be scared with all of it. Okay. So they have developed various, you can tell or you can go.
Where do you want me to go?
Okay, wait, I'll try to share and share the entire screen. How come this is? Yeah. Okay, fine.
That's on that system.
Okay. So you can see this, right?
Yeah.
So you just go for TopCat and also add astronomy. So you will see this thing, bliss.ac.uk. It is a TopCat. And what's happening here? You also share it.
I showed them this already.
No, it's your screen.
Okay, I want.
Yeah, so you see, you go here and you require Java to run this. This is so download it. You have jar file from Mac OS, Linux. So there are various ones. So whichever operating system you are using, you download that file. Okay, jar file. And this TopCat full.jar or TopCat. So yeah, okay, so you download it and you install it. Okay. So tomorrow we'll have sessions on this TopCat. TopCat allows you to see tables. So virtual observatories have defined certain protocols, table access protocol, which is STAC protocol, right? Simple image access protocol, SIAP, right? Then SSAP, simple spectral access protocol. So there are these terms which allows you to access spectra, access tables, access catalogs, and so on and so forth. Then there is something called SAMP, SAMP. SAMP is something which connects these things. So Aladin, which Priya just showed, you can see images on that. Aladdin is to look at images. This TopCat is to analyze tables. You can download tables of a cluster or a galaxy or an object, and you will have multiple columns and multiple rows. And TopCat allows you to say make plots, make histograms, select regions of it, define some mathematical functions between column one and column two and so on. So we'll be doing, only 3 people have said what TopCat is, but today you go home and install TopCat in your system, Linux, Windows, whichever version you have. And it's very simple and very intuitive for you to learn. but things, there are more serious aspects to it too. For example, there are cone searches. You can go into the VO button and you can have a cone search where you can look at a certain region in space and so on. And then you can connect an image and a catalog and objects. So there's an interoperability between different tools. Okay. So so either you can do astronomy by downloading data from the archives where you are, download it and use these tools to analyze it and make sense, to analyze spectra, to analyze images or whatever. Another very good way of doing it is PyVO, right? So Python, uh, like you all are familiar with Python. So PyVO is there one model is called AstroPy. How many of you are familiar with AstroPy? Yeah. So exactly like you have pandas and you have NumPy and so on, you have something called AstroPy. And if you need help in that, we can have sessions with you, but there are some who already know it. If you want it, just write to Priya and then we can have some very introductory small sessions and share the notebooks with you so that you can do. So this AstroPy is a collection of all those tools and things which you require to analyze astronomy and astrophysical data, right? It has ways of reading tables. So virtual observatories, they decided that tables should be shared in a certain format which is called VO tables. And Python allows you to save data, read data from your table or write it into that. Okay. Then it has ways where you can call Aladin from within it. It has sky coordinates, which allows you to convert from RA depth to alt azimuth or galactic very simply. It permits you to convert light years into kilometers or and vice versa in a very simple way. So AstroPy saves you a lot of time which you would otherwise spend a lot of time doing it. Okay. In that further, there is this Pi VO where for virtual observatories, it's a bundle of programs and protocols from which you can access images, access data. You can see, you have already seen that in action in what Surhud did. But specifically, if you want, we can have certain sessions or we'll share with you some Jupyter notebooks, which you can try to run yourself at work. Or tomorrow we'll have some session on PyVO. Okay, fine. So yeah, so the advantage of this PyVO is these days if you query on one object, say M31, you have tremendous amount of data on M31 because M31 has been observed by various surveys. There's SDSS which has done it, there's Gaia which has done it, the Plumas, in various surveys you have spectra on this and so any search which you make will lead to millions of or hits for that object, right? And PyVO makes it convenient for you to handle this tremendous amount of data. That's the basic idea in this. And another thing is, instead of downloading all the data from various sites, PyVO allows you to sample, take previews of one and decide which is the spectra you are interested in or which image, and then just download them. Or you can go on the cloud and work on the cloud rather than downloading and messing up your system because it is tremendous amount of data which is available. So it's not possible for our laptops to hold. So instead we log on to the servers, you can have some space allocated for yourself there. And so we'll be looking at TopCat. Then there is one more which is called DS9. DS9 again, DS stands for Deep Space Nine, but it's nothing to do with deep. The people who made it, they were interested. I think these are from Star Trek. Yeah. So there was a big fan of Star Trek, so Deep Space. So DS9 is again a Java applet which you can download it, and then you can analyze data, and there is interoperability. There you can talk from DS9 to TopCat to Aladin, vice versa. So yeah, so this is DS9. You can put image servers and okay, so we have some sessions on how to yeah. So you need to know what is the RA deck of this object. You just give the name and you retrieve and it gets it. You specify how many half minutes or how many degrees of that RA deck. You know what RA deck is, right? Right expression declination. These are the tests which we use to define objects. The simplest one which they people use is azimuth. At what altitude an object is and what is the azimuthal angle. That is from north how many degrees. So if you have an object, you drop it on the horizon, you drop from pole star to the horizon, yes, so you give the azimuth one, and how much above gives you the altitude. But altitude and azimuth of an object changes when you go from one location to another because Earth is ground. The horizon keeps changing. This would be the plane which is tangential to the Earth where you are standing is the horizon. So a person on 17 degrees horizon will be different from a person who is on 90 degrees, right? So if I say a comet is at 45 degrees, so many distance from Earth, you may not find it at all if you are at a different location. So there is another coordinate system which is right ascension and declination. We take the pole star axis to the pole star as the primary axis and take a plane which is perpendicular to that, which is called the celestial equator. And then you measure the angle from this celestial equator and the first point of gauge. So that R and D are basically sky coordinates. And the sky coordinates remain the same for all people around the world on a globe. So, yeah, so this is what Priya is showing. You can even stack up many images. You can see them in different filters. You contour plots, ISO, it's region with same intensity. You can take the radial density profiles and you can analyze the finer features of a galaxy or an object, which your naked eye will not show. So it can show you how the light falls in, and by looking at a different way the light falls of the bulge, it kind of tells you how that galaxy has been formed, whether it is a major merger thing or whether it's relaxed, right? So I think for today you have had enough, and we stop for today. And you download DS9, download TopCat, play around with TopCat, and tomorrow March
Aladin.
and Aladin. Okay. So if you just look for Aladin, it will give you a lot about that Aladin and the lamp and so on. So when you search for Aladin, say Aladin astronomy, then it will get you to the right side. So one other thing is you can directly work through your browser without installing it. It's a light version. Otherwise, you can download it and run it. If it is not running, it could be because you don't have Java installed. So you install Java and then everything will be fine. Okay, so I think we stop for today.
Yeah, 6 o'clock. 9 to 6 is a
And-
long day.
And sorry for those who were in HRDC guest house and there was the light problem. It generally doesn't happen in our campus. There was a transformer breakdown just outside the gate